In this lesson, we want to review the imaginary unit I. In elementary algebra courses, we typically don't deal with the square root of a negative number. If we see something like the square root of negative 25, we know that using the real number system, we can't get a solution, right? So a lot of times we would see this and we would stop and say no real number or no real solution or something like that. But as we progress through algebra, we learn that there is a way to kind of deal with this scenario. So the problem lies in the fact that we cannot square a real number and get a negative. If I take something like x, and this can be any real number, and I square it, the result is always greater than or equal to 0, okay, for any real number. If I square 0, I get 0. If I square a negative, I get a positive. If I square a positive, I get a positive. Okay, so it's not possible to square a real number and get a negative. So in order to kind of progress and deal with this scenario where we're taking the square root of something like negative 25, we introduce the imaginary unit I. So the definition of I is usually given as I squared is equal to negative 1. So this is now a number that when squared gives us a negative, and specifically a negative 1. Okay, you may also see that I is defined to be equal as the square root of negative 1. And this just comes from taking the square root of both sides here, right? If I took the square root of this side, I'd have just I. If I took the square root of this side, I'd have the square root of negative 1. So using this definition, and specifically we're going to focus on this one right here, we can rewrite the square root of negative 25 using the product rule for radicals. We'll say this is the square root of negative 1 multiplied by the square root of 25. We know the square root of negative 1 is defined right here to be I, okay, this imaginary unit. So I'm just going to replace that with an I. So I will have I times the square root of 25. We know the square root of 25, or at least the principal square root of 25 is 5. So I'm going to say this is 5 times I. Okay, so in this particular case, by using an imaginary unit I, I'm able to kind of push past my restrictions with real numbers and get a solution. Okay, so the square root of negative 25, we simplified that to 5i. So in general, we can use this rule here. We have the square root of negative a, and we say this is equal to I, okay, the imaginary unit, times the square root of a. All we're doing here, we're first assuming that a is a positive real number, and we're saying the square root of negative a is equal to the square root of negative 1, right? I'm just dealing with this negative right here, times the square root of a. So this is equal to, this by definition is I, so I put the I here, and then times the square root of a. Now, you typically see the I written in front of the square root symbol. Why is that the case? Well, a lot of times, if you put it like this and you say the square root of a and then multiplied by I like that, you might make a mistake and then extend the radical a little too far. It may be confusing in terms of where it is. So to clarify things, we just put the I out in front. Okay, so that's why you see that. But it is not incorrect to do the square root of a times I like that. But you will not typically see that. All right, let's start out with the square root of negative 100. So kind of the long way to do this is to break it up, again, using the product rule for radicals. I can say this is the square root of negative 1 times the square root of 100. Again, we know by definition that the square root of negative 1 is I. So I'm going to replace that with just I, and then times the square root of 100. The square root of 100, or at least, again, the principal square root of 100 is 10. So I can say this is I times 10, or 10i, and that's simplified. Now, how can I speed up this process? So let's say that I saw the square root of negative 100. We know that this negative here is basically negative 1. So if I have the square root of negative 1, I know I can pull that out and say that's I. So anytime you see a negative involved and it's underneath a square root symbol, just go ahead and pull that part out and say, okay, this is I times, this number here is 100, so I times the square root of 100. And then I'll go ahead and just say this is I times 10, or 10i, okay? You don't need to go through this long process each time. This is just to demonstrate where things are coming from. All right, let's take a look at another one. So we have the negative square root of negative 64. So this negative out in front is just going to carry itself over here. Once we've done that, we don't need to worry about it anymore. This negative inside of the square root symbol is different, right? That is representing the square root of -1. We're going to replace that with just I. Now, I would think about this as times the square root of 64. Square root of 64 is just 8. So I can wrap up this problem and say that I have 8 times -I, or negative 8I, as my simplified answer. What about something like the square root of -24? So again, the first thing I'm going to do is realize that I can pull that negative out, right? I can think about that as, again, the square root of -1, which is I, and then times the square root of 24. The square root of 24, you think about 24 as not being a perfect square, right? There's no rational number that you can square to get 24. But one of the factors of 24 is a perfect square, right? 24 is 4 times 6. 4 is a perfect square. So I can say this is I times the square root of 4 times the square root of 6. Square root of 4 is 2. So I'm going to go ahead and say this is 2I times the square root of 6. All right, let's take a look at kind of a trap question that you're going to get. So suppose we had the square root of -9 times the square root of -16. What would you do to simplify this? Well, a lot of people would look at this and say, okay, I'm going to use my product rule for radicals. I'm going to have a square root, and I'm just going to take these radicands here, and I'm going to combine them under this square root symbol. So -9 times -16. We know -9 times -16 is 144, right? So this would be the square root of 144. And if we take the square root of 144, we end up with 12, okay? So you might put that down as your answer. But the problem is this is absolutely wrong, okay? This is wrong. The reason is that when we use the product rule for radicals with two negative radicands, it doesn't give us the correct answer, okay? So we can't use our product rule for radicals with two negative radicands. We can use it with two positive radicands. So if these were both positive, we could do this, right? This would be square root of 144, which would be 12, so that would be correct there. Or we could do it with one negative and one positive, okay? So there can be alternating signs. It will work in that scenario. For this case, what I would end up doing is pulling the negative out of this part and saying I have an I times the square root of, you'd have 9 times 16, which is, again, 144. So this equals square root of 144 is 12, so this would be 12I. Okay, that would be the correct solution. That's fine. But again, if you use two negative radicands, you cannot use that rule. So what you need to do in this scenario is convert each of these first. So I'm going to pull the negative out of each part and say this is I times the square root of 9 times, you'll have I times the square root of 16. Once you've done that, then you can use your product rule for radicals. It's fine now because you have square root of 9, 9 is a positive number. You have square root of 16, 16 is a positive number. So there's nothing else that's stopping you there. So I times I is I squared. And then we know that the square root of 9 times the square root of 16, we could put the square root of 144. So this is going to equal I squared times the square root of 144 is 12. Now, most people will stop and write this as 12I squared. But we should know from the beginning of the lesson that I squared is defined to be equal to -1. So anywhere I see I squared, I can just replace it with -1. So if I had 12 times -1, this would be -12, okay, and that would be my answer. So notice how I got -12 here, whereas if I went with the product rule for radicals, I would have ended up with a positive 12, okay? So it's a very different answer in terms of the sign. So you've got to make sure that if you have two negative radicands, you simplify using this method, right? Pull the -1 out of each one of those guys, and then you can use the product rule for radicals. So let's look at another example. Suppose we have the square root of -6 times the square root of -5. Again, all I'm going to do, because I have two negative radicands here, I'm going to pull this out of each. So I'll have I times the square root of 6 multiplied by I times the square root of 5. So I times I, again, is I squared. And then times square root of 6 times square root of 5. Really, you can just write that as a square root of 30. We know that I squared is -1. So I can go ahead and say this is negative square root of 30. All right, let's look at another one. So we have the square root of -8 times the square root of -11 times the square root of -3. So again, to simplify this, I want to change I want to change each of these, okay? So I'm going to have I times square root of 8 times I times square root of 11 times I times square root of 3. Okay, what's that going to give me? Well, I know I can simplify the square root of 8. 8 is 4 times 2, so I can say this is I times square root of 4 times square root of 2 times I times square root of 11 times I times square root of 3. Okay? So essentially, we know at this point that the square root of 4 is 2. So I'm going to say I have 2 I times I is I cubed. And then you're going to have square root of 2 times square root of 11 is square root of 22. Square root of 22 times square root of 3 is square root of 66. Now, I can simplify I cubed. And we'll talk more about this in another lesson. But essentially, using my rules for exponents, I cubed is what? I can say this is I squared, which I know is -1, times I to the first power, or just I. So I can replace this part right here with a -1, and then say times I, which is just negative I. So I'm going to erase this. I'm going to put the negative part of that out in front, and just put an I right there. So this would simplify to -2i times the square root of 66. So when we work with dividing radicals, we're going to use the same process. If we have two negatives involved, we need to change each form first, okay? So the square root of -15, we're going to write as I times the square root of 15. And then the square root of -3, we're going to write as I times the square root of 3. And I can go ahead and simplify this further. Square root of 15 is what? It's the square root of 5 times the square root of 3. This is over the square root of 3 here. And then I've got I over I. Now, I know these are going to cancel. I over I, doesn't matter, that's an imaginary unit. Same thing over itself. As long as it's not 0, that's allowed, and it cancels to be 1. Over here, square root of 3 over square root of 3, again, same non-zero number over itself, that cancels and it's 1. So here I'm just left with the square root of 5. In this lesson, we want to review operations with complex numbers. So in our last lesson, we reviewed the concept of the imaginary unit I. Again, the definition of I is given as I squared is equal to -1. Or alternatively, you could say that I is equal to the square root of -1. So if we look at something like A plus BI, where we would say that A and B, these two guys are real numbers. And again, I represents the imaginary unit. When we see A plus BI, this is known as a complex number. Okay, so this whole thing together, we're going to say is a complex number. Now, in your textbook, when you see something written as A, some real number, plus B, another real number, multiplied by I, again, the imaginary unit, this is known as standard form for a complex number. So something like 3 plus 7i, or something like -2 minus 9i, right? So on and so forth. This is in standard form. You want the real part, which is this part right here. So this is the real part, because it only consists of a real number. And then this part right here, this BI part, is last. This is your imaginary part. So this is the imaginary part. Now, some textbooks will differ on this. They'll only call B the imaginary part. So you just need to be aware that from textbook to textbook, from teacher to teacher, they might say something different. But generally just go with whatever your teacher or your textbook is saying. Okay, so it's either that BI is the imaginary part or just that B is the imaginary part. Now, when we work with complex numbers, we need to understand that the real numbers are a subset of the complex numbers. What do I mean by that? Well, I can take any real number that I want and write it as a complex number. Let's say I had the number 3. I could put this as 3 plus, for my B there, I'd use a 0, and then times I. 0 times anything is always 0. It doesn't matter if I'm multiplying it by I. It's the same. So this would be just 3, right? I'd have 3 plus 0, which is just 3. So I took a real number 3, and I wrote it as a complex number, 3 plus 0i. So again, that tells us that the real numbers are a subset of the complex numbers, right? They're part of them. As another example, I could take something like negative 16, and I could write it as negative 16 plus 0i. And again, this is just negative 16. This is the same thing as when we took integers and we showed that we could write them as rational numbers. Because we could say all integers are rational numbers, right? So if I took, let's say, negative 12, I can always write this as negative 12 over 1, and this shows it as a rational number. But not all rational numbers are integers. I can't take something like 2/3 and write it as an integer, okay? So it's the same concept here. All real numbers are complex numbers. You can write them as plus 0i, so 3 plus 0i is 3, negative 16 plus 0i is negative 16, so on and so forth. But not all complex numbers are real numbers, okay? The complex numbers include more numbers, okay? They're a larger set. So I could do something like 2 plus, let's say, 5i. This is a complex number. I cannot write this as a real number. So when we work with complex numbers, we use the same properties to simplify things. So if I saw something like the quantity negative 3 plus I, then plus the quantity 2 plus 5i, I would just arrange the real and the imaginary parts together. So in other words, I would use my associative and my commutative properties to kind of reorder this. I could say this is negative 3 plus 2. Those are the real parts. Then plus, you have I plus 5i. So I plus 5i, those are the imaginary parts. So we could say negative 3 plus 2 is negative 1. And then plus, you have I plus 5i, which is 6i. So you end up with negative 1 plus 6i as your answer here. And notice how we give our answer in the format of A, the real part, plus your B, which is 6 in this case, times I. Okay, this is the imaginary part, this is the real part. So this is your standard form, right? Some people will kind of switch this around and say this is 6i minus 1. This is not standard form, okay? You want the real part first. That's why we have negative 1 out in front. Then plus your imaginary part, the 6i, second. All right, let's take a look at another one. So suppose we have the quantity 8 minus 3i, then minus, we have the quantity 2 plus 4i, then minus, we have the quantity 2 plus 6i. So what I want to do here, let me just distribute the negative to each term. I'm going to put plus negative 1 here and plus negative 1 here. So I'm going to write this as 8 minus 3i. Then negative 1 times 2 is minus 2. Negative 1 times 4i is minus 4i. Negative 1 times 2 is minus 2. Negative 1 times 6i is minus 6i. So we can regroup these if you want. At this point, you should understand that you can add the real parts together and the imaginary parts together. So in other words, I can say 8 minus 2 minus 2. 8 minus 2 is 6. 6 minus 2 is 4. But if it helps you, you can group it like this. 8 minus 2 minus 2. And then plus, you've got your imaginary parts. So you've got your negative 3i. You've got your minus 4i. And you've got your minus 6i. If you need to group it like this for a while, that's fine too. It's just a little bit slower. So again, 8 minus 2 is 4. So that's your real part. Then plus, negative 3i minus 4i is negative 7i. Negative 7i minus 6i is negative 13i. So let me just put minus 13i. And again, it's written in standard form where your real part is first, your 4. This is your A. And then you have plus. In this case, you'll have negative 13 that represents your B. And then you have I. So this part right here is going to be your imaginary part. So the real part comes first, imaginary part is second. All right, let's look at some multiplication problems. Pretty simple to do this. We're just going to use our FOIL method because we have the product of two binomials. So we have the quantity 6 plus 6i times the quantity 4 plus 6i. All I'm going to do here, first term, 6 times 4 is 24. My outer terms, 6 times 6i is plus 36i. Make that a little better. Then plus 6i times 4 is plus 24i. And then last, 6i times 6i is plus 36i squared. Okay, so what can we combine? The 24, I can't do anything with that for right now. We'll be able to do that with something with it in a second. But for right now, nothing. 36i plus 24i. 36 plus 24 is 60. So this would be plus 60i. And then 36i squared. Remember, I squared is defined to be negative 1. So I can go ahead and say this is plus 36 times negative 1, which is basically minus 36 or negative 36. So I can erase this and put minus 36. And now I can combine 24 and negative 36 as negative 12. So I want the negative 12 out in front, because that's the real part. Then plus, I want the 60i in the back, because this is the imaginary part. So negative 12 plus 60i is your answer in standard form. All right, let's take a look at a longer one. So we have the product of three binomials here. So I'm going to use FOIL with the first two, and then I'll take that result and I'll multiply it by the final binomial. So we'll just start with these guys right here. So what does that give us? So 5 times negative 6 would be the first terms. That's negative 30. The outer 5 times 6i is plus 30i. The inner 3i times negative 6 is minus 18i. The last 3i times 6i is plus 18i squared. Now, we know I squared is negative 1. So let's go ahead and erase this and put a minus 18. So to combine things here, negative 30 minus 18 is negative 48. So negative 48. Then we know that 30i minus 18i is going to give us 12i. Okay, so let's erase this. So we're going to put this in parentheses, and we'll drag it up. And now it's times this guy, negative 1 minus 3i. Okay, so let's do the FOIL again. So negative 48 times negative 1 is positive 48. Then negative 48 times negative 3i is plus 48 times 3 is 144, and then times I. Then you'd have 12i times negative 1, which is minus 12i. And then lastly, you would have 12i times negative 3i. That's minus 36i squared. Let me make that a little better. All right, so let's wrap up the problem now and do some simplifying. We know that I squared is negative 1. So if I had a negative 1 times this negative here, this would become positive, okay? So 48 plus 36 is 84. So this is 84 plus 144i minus 12i is 132i. So again, our answer here in standard form is 84 plus 132i. All right, so let's talk a little bit about dividing with complex numbers. You need to be aware that, again, the definition of I is that it's equal to the square root of negative 1. So if I have negative 7 over 5i, this is really like saying I have negative 7 over 5 times the square root of negative 1. We know that a simplified radical expression does not contain a radical in the denominator. So we want to rationalize this guy. And so we can multiply both the numerator and denominator by the square root of negative 1. But typically what we'll do is just keep it in this format of I. So I'll do I over I, right? So in the numerator, I'll have negative 7i. In the denominator, 5 times I is 5i squared. We know I squared is negative 1. So this would basically be what? Negative 7i over negative 5. Negative over negative is positive. So you end up with 7i over 5. Now it's okay that I is in the numerator because, again, you can have a radical, the square root of negative 1, in the numerator. You just don't want it in the denominator because it's not considered simplified. All right, let's take a look at another one. So we have 9 plus 4i over negative 5i. Again, I've got I here in the denominator. So to get rid of that, I'm going to put I over I here and multiply by that. So I've got to use my distributive property. I times 9 is 9i. Then plus 4i times I is 4i squared. And we know that's negative 1. So you can go ahead and just replace that and say this is negative. Okay. Anytime you get I squared, just immediately replace it with negative 1 and see what that gives you, because you don't want to have to worry about simplifying it later. It might be something you just forget. So then down here, negative 5 times I times I times I is I squared. So the negative 5 times negative 1, right, that's I squared, would give me positive 5. So there's really nothing else I can do to simplify here. You'd just be left with 9i minus 4 over 5. If you wanted to, for the sake of writing this in standard form, you could reorder this. First, you could break it up as 9i over 5, then plus negative 4 over 5. And then you want the real part out in front. So you would go ahead and say this is negative 4/5, that real number, then plus your imaginary part, which is going to be the 9i over 5. So again, if you wanted to write this in standard form, you would want to break it up like this. You've got your real part of negative 4/5 plus your imaginary part of 9/5 times I. All All right, so the last concept we're going to go over is basically rationalizing with a binomial denominator that includes a complex number. All right, so we previously learned that conjugates were the sum and difference of the same two terms. So something like the quantity a plus b times the quantity a minus b. So you've got a and a, you've got b and b, different signs, right? Plus and minus. If we were to FOIL this out, the middle two terms drop out. You've got a squared minus b squared. Okay, so nothing new there. When you do this and you have I involved, like a plus bi multiplied by a minus bi, the sign is going to change. It's because you're going to end up with an I squared, and the I squared is -1, and so it flips the sign. So first terms here, a times a is a squared. Your outer, a times negative bi is minus abi. Your inner, a times bi is plus abi. You can see those would cancel, right? They're basically opposites. You've got minus abi and plus abi. You can erase that. You don't need it. Then we've got positive bi times negative bi. We know that's a negative. B times b is b squared. And I times I is I squared. Okay? We know I squared is -1. So if I replace this with -1 here, again, you can think about this as plus a negative here. Negative times negative is positive. So this is going to be a squared plus b squared. Okay, so that's where that comes from. So we're going to use this part right here to help us simplify a two-term denominator when I is involved. So let's look at an example we already know how to deal with. So if we saw something like 8 over, you have 3 minus the square root of 5. We should know at this point that if we have a binomial denominator here, we can multiply the numerator and denominator by the conjugate of the denominator. So I would just multiply by 3 plus the square root of 5 over 3 plus the square root of 5, right? This is going to clear my radical from the denominator. In the numerator, 8 times 3 is 24. Then plus, you'd have 8 times square root of 5. In the denominator, 3 times 3 is going to give me 9. So then the outer and inner would cancel. You'd have 3 times square root of 5 and then -3 times square root of 5. So those would cancel. And then lastly, you would have minus. We know the square root of 5 times square root of 5 would be 5. So let's finish this up. We would have 24 plus 8 times square root of 5 over 9 minus 5 is 4. Now you can simplify this further because you can factor out a 4 from the numerator. So if a 4 got factored out, inside you would have a 6 plus 2 times square root of 5. And this is over 4. I can cancel this with this, and I'd be left with a simplified answer of 6 plus 2 times square root of 5. Now, we're going to use the same thought process for this example here. So we have 9i over, you have -5 minus 7i. So I want to get rid of this guy right here because it represents a radical of square root of -1 in the denominator, okay? So what I'm going to do is I'm going to multiply the numerator and denominator by the complex conjugate. So it's the same concept. So I'm going to take this guy right here, the -5. I'm going to take this guy right here, the 7i. I'm just going to flip the sign. So it's negative, it's going to become a positive, right? If it's subtraction, it becomes addition. If it's addition, it becomes subtraction. Okay, that's all you're doing. So over here, I have the same thing, -5 plus 7i. And what happens is when I multiply in the denominator, I don't need to go through FOIL. I just showed you that if you have a minus bi times a plus bi, it's a squared plus b squared, okay? So a is -5. If I square that, I get 25. Then plus b is 7, okay, and 7 only. If I square 7, I get 49. And you can pause the video and verify that for yourself, but that is what you get. Remember, I times I is I squared, and that represents -1. Okay, so that's why you get a different sign. In the numerator, 9i times -5 is -45i. Then we have 9i times 7i. That would be plus 63i squared. Okay, let's see what we can do to simplify. Well, we know I squared is -1. So I'm going to start out by just writing this as -63. And then minus 45i. And this is over. 25 plus 49 is 74. Now, is there anything at this point that I could cancel? So I would have to be able to pull something out from this and this that could cancel with this. Okay, so there's really nothing else you can do. But we do want to split this up and say this is -63 over 74. And then I'm going to say plus, you have negative 45 over 74 times I. Again, this part right here, your negative 63 over 74 is the A, or the real part. And then this part right here, this is your B, right? Your negative 45 over 74, and then you have your I. So you've got your real part and your imaginary part. Again, the real part goes first. That's how you put it in standard form. So negative 63 over 74 plus negative 45 over 74 times I. All right, let's take a look at one more of these. So we have 6 minus 6i over, you have 2 plus 3i. Again, the idea is I want to get rid of this I in the denominator because it represents a radical in the denominator, so this is not currently simplified. All I need to do is multiply the numerator and denominator by the complex conjugate. So 2 and 3i, just change the sign. Right now it's a positive or a plus, so you could say this is going to be a negative or a minus. Okay, so 2 minus 3i. All right, so now we just do our multiplication. Again, just use the formula down here, it's faster. If I had 2 plus 3i multiplied by 2 minus 3i, again, it's a plus bi times a minus bi. Okay, so it's a squared plus b squared. Okay, 2 is a, 2 squared is 4. Then plus, 3 is b, 3 squared is 9. We know 4 plus 9 is 13, so let's just go ahead and write that. So the denominator's done, we don't need to do anything else. In the numerator, we've got to use our FOIL. Okay, so we've got 6 times 2, that's 12. The outer would be minus 18i. The inner would be minus 12i. So let's go ahead and combine that. We know that would be minus 30i. And then for my last, I would have a negative 6i times a negative 3i. We're going to go ahead and say that's a plus. 6 times 3 is 18. And then we would have I times I, which is I squared. Now we know that I squared is negative 1. So that would be negative 18. So we can basically say this is minus 18. And then 12 minus 18 is negative 6. So let's go ahead and erase that and that. And let me erase this and say this is just negative 6 minus 30i over 13. Again, to put this in standard form, I'm going to break it up. I'm going to say this is negative 6 over 13. Then I'll put plus, you'll have negative 30 over 13, and then times I. Okay, so this is your real part. This is the A. This is the B part. Okay, this is what's multiplying I. But the whole thing, the negative 30 over 13 times I, is the imaginary part. But again, some books go back and forth on this. So standard form, I'm just going to say, is negative 6 over 13 plus you have your negative 30 over 13 times I. In this lesson, we want to review simplifying powers of I. So over the course of the last 2 lessons, we talked about the imaginary unit I, and we talked about complex numbers in general and how to perform operations with complex numbers. So one more topic that comes up when you first start looking at imaginary units, you're going to think about how to simplify powers of I. So if you got something like I raised to the power of 503, you are expected to write that in a simpler form, okay? So it's very easy to kind of perform this simplification. You just need to know your rules of exponents, and you need to know the first 4, so I to the first power, I squared, I cubed, and I to the 4th power, so the first 4 powers of I, okay? With those 2 things, the rules of exponents and the first 4 powers of I, you can simplify any power of I that you'd want to. All right, so the first thing I have listed here is I to the power of 0 is equal to 1. I just put this here for reference sake. We're not going to use it in the lesson. A lot of students will ask, is I to the power of 0 equal to 1? The answer to that is yes. So any non-zero number raised to the power of 0 is always 1, okay? When we think about the definition of I, we normally get I squared is equal to negative 1 given to us. So this guy right here. And we know that I to the first power is just equal to I, right? Any number raised to the power of 1 is just itself. So that's where those 2 come from. Now, when I get to I cubed, I start using my rules for exponents. So I break this up and I say it's equal to I squared times I. Okay, you can say this is I to the first power here if you want to. By rules of exponents, if I multiply here, I stays the same and I add 2 plus 1 to get me back to 3. Okay, so I haven't done anything illegal. Then I take the fact that I squared, by definition, is negative 1, and I just replace it. So now I have negative 1 times I, which is just negative I. Okay, so right now we know that I to the first power is just I squared is negative 1, and I cubed is negative I. Now, what about I to the 4th power? We're going to break this up as I squared times I squared. Again, rules of exponents, I would stay the same. 2 plus 2 is 4, so nothing illegal there. And again, we know that I squared, by definition, is negative 1. So we're just replacing it in each case. Negative 1 times negative 1 is positive 1, okay? So we need to write this down in your notebook or whatever you're using to follow along. I to the first power is I squared is negative 1, I cubed is negative I, and I to the fourth power is 1. So we just need to know those four, okay? That's all we need. So let's look at our first example. So suppose we see I to the power of 48. So the first thing you're going to look for, if you're dealing with whole number exponents, okay? Whole number exponents. So if you have something like 48, which is a whole number, the first thing you want to do is check for divisibility by 4. If it's divisible by 4, it's equal to 1, okay? So 48 is divisible by 4. 48 divided by 4 is 12. So I can rewrite this using the power to power rule as I to the fourth power raised to the 12th power, okay? If I know that I to the fourth power by definition is 1, then I could say this is 1 to the 12th power, which is 1. So if you have I raised to a whole number exponent that is divisible by 4, it simplifies to just 1. So if I had something like I to the power of 60 as an example, we all know that 60 divided by 4 is 15. So I could write this as I to the fourth power raised to the 15th power. Again, this is just 1 to the 15th power, which is 1. 1 raised to any power is always 1. Okay, so it doesn't matter what you're raising it to. Once you have this I to the fourth power here being raised to something, it's just 1 raised to whatever, which is always going to give you 1. Okay, if you had something like I raised to the power of 200 as an example, we know that 200 divided by 4 is 50. So again, I could just say that this is I to the fourth power raised to the 50th power. This is 1 raised to the 50th power, which is just 1. Okay, so if you have I raised to a whole number exponent, and that whole number happens to be divisible by 4, it's just equal to 1. Okay, you don't need to do all this. You can just stop and say it's 1. Now, what if it's not divisible by 4? What do we do? So suppose we saw I raised to the power of 61. Well, what you want to do is you want to look for the next number going down that's going to be divisible by 4. Okay, so in this case, we know that if you're at 61, if I go down to 60, 60 divisible by 4, 60 divided by 4 is 15. So I'm just going to break this up and say this is I to the power of 60. Let me make that a little better. So again, I to the power of 60 times I to the first power. Now, we know I to the power of 60 is what? It's 1, right? I could write it as I to the power of 4 raised to the power of 15. This is 1. So I can replace this right here with a 1. That's gone. Don't even think about it anymore. So it's 1 times I to the first power, which is just I, okay? Very, very easy process. All right, what about I to the power of 202? Again, is it divisible by 4? No, it's not, right? A number for it to be divisible by 4, the final 2 digits, in this case that would be 2, because there's a 0 in front of the 2, has to form a number that's divisible by 4. 2 is not divisible by 4, right? If I divide 2 by 4, I get 0.5. So what I have to do is, again, look for a number going down that's divisible by 4. 201 wouldn't be, but 200 is. So I can break this up and say this is what? It's I to the power of 200 times I squared. Okay, we know that this guy is going to be a 1, right? So we'll say 1 times I squared. And we know that I squared, by definition, is negative 1. All right, what about I raised to the power of 1003? Okay, we know that, again, I look at the final 2 digits of the number. It's a 3. It's not divisible by 4. If that was a 4, it would be, but we're not that high up. So we need to go down to 2, which isn't, and then to 1, which isn't, and then to 0, which is. So the number 1000 is divisible by 4. So I could write this as I raised to the power of 1000 times I raised to the power of 3. We know this is 1, okay? So 1 times I cubed. Again, we know by definition I cubed is negative I. Okay, so this is negative I. All right, what about I raised to the power of negative 22? Don't get scared if you see a negative exponent. Remember, if you get a negative exponent, you take the reciprocal of the base, okay, so it would be 1 over I, and you make the exponent positive, so it's to the 22nd power. So again, I'm just using my same process here. So I have 1 over, when I think about I to the power of 22, is 22 divisible by 4? No. Is 21? No. Is 20? Yes. So I can write this as 1 over I raised to the power of 20 times I raised to the power of 2. Okay, so 1 over, I know I raised to the power of 20 is 1, times I squared is negative 1. So times negative 1. So you basically have 1 over, 1 times negative 1 is just negative 1. So 1 over negative 1, which is negative 1. All right, let's take a look at one more. So we have I raised to the power of negative 119. So again, what do I do with a negative exponent? Reciprocal of the base, make the exponent positive. Okay, not that bad. Let me make that 9 a little better for you. All right, so what are we going to do? Think about, is 119 divisible by 4? We'll just look at 19. 19 is not divisible by 4, so go down. Is 18 divisible by 4? No. Is 17? No. Is 16? Yes. So 116 would be divisible by 4. So I can break this up and say this is 1 over I raised to the power of 116 times I cubed, right? Because 116 plus 3 would be 119. Okay, so this right here is going to be 1. So I'll put is equal to 1 over 1 times I cubed. We know by definition that I cubed is negative I. So we'll put 1 over negative I. And you can leave it like this, or you could put negative 1 over I, or you could put negative 1 over I. Remember, when you have a negative involved with a fraction, the numerator can be negative and the denominator can be positive. Or you can say that the numerator is positive and the denominator is negative, or you can just put a negative out in front. Okay, all of those work. So I can also just say, if this guy is out in front, and make that clearer, I can also say this is a negative 1 over I. All three of these mean the exact same thing. So the simplified version, you could just pick one of those. As it says, I'll just say it's 1 over negative I. In this lesson, we want to review solving quadratic equations by factoring. So in this section of the course, we're going to review how to solve quadratic equations. So for most of you that took lower level algebra courses, you already understand that there are multiple methods to kind of achieve this task. The easiest case scenario is when we can solve a quadratic equation using factoring, okay? But we cannot use this method every time, so we've got to have other tools like completing the square and the quadratic formula. So we'll talk about those other methods over the course of the next few videos. In this lesson, we want to focus on just solving quadratic equations by factoring. So first and foremost, let's explain standard form for a quadratic equation. So in your textbook, when you first start talking about quadratic equations, you'll see something like this. We have ax squared plus bx plus c is equal to 0. And we basically restrict a, the coefficient of x squared, and we say it can't be equal to 0. And the reason for that lies in the definition of a quadratic equation. With a quadratic equation, you have a variable like x that's squared, and you don't have a variable that's raised to a higher power. So you don't have like x cubed or x to the 4th power or anything like that. So x squared, the 2 is the highest exponential power on the variable. When you work with a quadratic equation, it's also known as a second degree equation for that reason, right? Because again, the highest exponential power is a 2. When we think about a polynomial, if the highest power on the variable is a 2, it's known as a second degree polynomial. When we look at these guys, we could say a, b, and c could be any real number with that one exception that a is not equal to 0. So something like 5x squared plus 2x plus 3 equals 0. Or something like, let's say, 3x squared plus, you could have 0x plus 2 equals 0. And this guy right here, this plus 0x, I can get rid of that and just say this is plus 2 equals 0. Okay, so this is still a quadratic equation because I've still got my variable raised to the 2nd power, so it still fits that definition, okay? And similarly, I could just put something like plus 5x equals 0. I don't have to have a constant term. That could just be 0. The main thing here is to understand how to write this in standard form. So this is in standard form, this is in standard form, and this is obviously in standard form here. So let me kind of notate this. This is standard form, okay? So you want it as a, some coefficient of x squared, plus b, some coefficient of x, plus c, the constant, is equal to 0. Okay, 0 is going to be on one side, everything else is on the other. In order to solve a quadratic equation by factoring, we have to understand something known as the zero product property, aka the zero factor property. Okay, so those are the same thing. This tells us that if two real numbers are multiplied together and the result is 0, so something like a multiplied by b equals 0, then essentially one of the following possibilities has to be true. we could have that A is equal to 0 and B does not equal 0. So something like, let's say A is 0 and B is, let's say, 2. 0 times 2 is obviously 0, right? 0 times anything is 0. It could also be true that A is not equal to 0 and B is 0. So let's say A is -5 and B is 0. This still gives us 0. Lastly, you could have that A is equal to 0 and B is equal to 0. So it could be we have 0 times 0, and that is obviously 0. Okay, so this is the kind of math behind what we're going to do today. This is in its simplest form. We're going to look at it in a more complex form. And to kind of see this, let's first start out by working through this problem. So we have x squared plus 4x equals x plus 28. So we want to solve this quadratic equation by factoring, meaning we want to find the values for x that make it into a true statement, okay? So the first thing I want to do is I want to write it in standard form. So my ax squared plus bx plus c is equal to 0. Now, it doesn't matter which side 0 is on, but typically you'll see 0 on the right side and everything else on the left. So let's just kind of follow that. So to accomplish this, I'm going to use my addition property of equality. I'm going to subtract 28 away from each side of the equation. I'm also going to subtract x away from each side of the equation. So on the right side, this is all going to cancel and just become 0. On the left side, I have my x squared. And then I have 4x minus x, so that's plus 3x. And then I have my minus 28. And of course, this is equal to, we already said the right side is 0. So now it's in the format of ax squared, in this case a is just 1, plus bx, in this case b is 3, plus c, in this case c is -28. Okay, so this equals 0. All right, so now that we have it in standard form, we want to factor it. Okay, we want to factor it. So let's drag this up here. And let's see how we can factor this. If it's a trinomial, we're trying to factor this into the product of two binomials. This is our easiest case scenario. So we have x squared here. So this would be x and this would be x. And I just need to work out what is this and what is this. So give me two integers whose sum is 3 and whose product is -28. Well, for positive 28, it's only 1 times 28 or 4 times 7. Okay? If you think about 1 and 28, there's no way to play with the signs and make that work. You can't get a sum of positive 3. But if you play with the signs with 7 and 4, you can make it work. If I had a positive 7 and a -4, 7 times -4 is -28. 7 minus 4 is positive 3. Okay? So now that we have factored the left side of this guy, what I want to do is think about, again, my zero product property. If A times B equals 0, then A can be 0 and B cannot. B could be 0 and A cannot. Or A and B could both be 0. Well, it's the same thing here. You've got to realize that these guys are factors. The quantity x plus 7 is multiplying the quantity x minus 4. So these are factors. These are factors. Okay, so make sure you understand that. So if I find a value for x that when plugged in here and here, let's just say makes this guy into 0, well, 0 times whatever this is will give me 0. Same thing over here. If I find a value for x that makes this guy into 0, 0 times whatever this is would also give me 0. So essentially, I just want to set each factor equal to 0, and I want to solve and find out what that value is. Those values will be solutions for my equation, okay? So I'm going to start out with x plus 7. That's one of my factors. And I'm just going to set that equal to 0. Very easy to solve this. I just subtract 7 away from each side of the equation. I get that x is equal to -7. So let me just kind of put this over here. We'll say that x is equal to -7. That's one of the solutions. I'll put a comma since I have a second solution. The other scenario is that x minus 4 equals 0. So x minus 4 equals 0. So I can add 4 to each side of the equation, and I'll get that x is equal to 4. Okay? So let me put a 4 right there. Now, when we check this, I want to show you in this kind of factored form what happens. Let's start out by checking x equals -7. If I plugged in a -7 for x there, what happens? You're going to have a -7 plus a 7. And then over here, you're going to have a -7 minus a 4. And then, of course, this is equal to 0. -7 plus 7 is 0. So this is where the magic happens. You have 0 times, doesn't matter what this is over here, it's going to work, right? Because 0 times anything is just 0. -7 minus 4 is -11. 0 times -11 is 0. So you get 0 equals 0. So we can go ahead and check this guy off and say it does work, right? -7 is the solution. And you can also check that in the original equation if you'd like. I'm not going to go through that just for the sake of time, but you can pause the video and plug in a -7 here, here, and here, and you'll see that you do get the same value on the left as you get on the right. Let's also check 4 in the factored form. So if I plugged in a 4 there and there, what would I get? Well, on the left side, I get 4 plus 7, which is 11. On the right side, I get 4 minus 4, which is 0. 11 times 0 is, again, 0. So you get 0 equals 0. So this results in a true statement. So this one works out as well. So our two solutions here are that x equals -7 or x equals 4. All right, let's take a look at another one. So we have 77x is equal to, you've got -15x squared minus 3x minus 105. So again, I want to write this in standard form. So we want ax squared plus bx plus c is equal to 0. So essentially, I want one side of the equation to be 0. And to accomplish this, I can just subtract 77x away from each side of the equation. On the left, I would just have 0. So 0 is equal to, you'd have your -15x squared. -3x minus 77x is minus 80x. And then you'd have your minus 105. So let's scroll down a little bit. Now, there's two things here. Most people like their 0 to be on the right. There's nothing wrong with just kind of flipping this around and saying this is -15x squared minus 80x minus 105 is equal to 0. Okay, that's perfectly legal. The other thing is you have negatives for each term here. If you don't want to deal with that when you're factoring, you can use your multiplication property of equality here. You can multiply both sides of the equation by -1. Multiplying 0 by -1 will still be 0. So if I multiply 0 by -1, I still have 0. If I multiply each term here by -1, I'm going to just change the sign. So I would have 15x squared plus 80x plus 105. Okay? So now this will be a little bit easier to factor. So now that we've written in standard form, we're ready to factor the left-hand side here. So the first thing I notice is that everything is divisible by 5 on the left. So we can go ahead and pull that out. That would give me a 3x squared plus a 16x plus 21, and this is equal to 0. All right, so we need to keep factoring here. So would have 5 times, I'll set up my parentheses. I know that this number here is prime, this 3, that's the coefficient for x squared. I'll do 3x and x. And now I just need to work out these two parts right here, okay? The outer and the inner have to sum to 16x, and the last have to give me a product of 21. So I need two of those integers that's going to fit the criteria there. Well, if I think about 21, this kind of final term here, it's only 1 times 21 or 7 times 3. So there's no way to make it work with 1 and 21, right? 1 and 21, no matter what I do, it would just be too large of a sum. But with 7 and 3, I might be able to make that work. I can't put my 7 here because 7 times 3 would be 21. That's already larger than 16, so that doesn't work. I'd have to put a 7 here and a 3 here. So does that work? Well, yeah, it does. Because my outer here would be 9x, and my inner here would be 7x. 9x plus 7x is 16x. So this is the correct factorization. All right, so once we have it in a factored form, remember what we did last time. We took each factor and we set it equal to 0. Well, here we have a factor of 5. We don't need to set that equal to 0 because that would just be nonsense. So we would kind of be more specific here and say we're going to set each factor with a variable in it equal to 0, and we're going to solve. So let's go ahead and take this left one first. So 3x plus 7 is equal to 0. We would subtract 7 away from each side of the equation. We'll get that 3x is equal to -7. We will divide both sides by 3, and we'll find that x is equal to -7/3. Okay? So let me just kind of write that over here. We'll say that x equals -7/3, and then we'll have another value for x that works. So let's work on this guy over here on the right. So now we have x plus 3. We're going to set that equal to 0. And we're just going to subtract 3 away from each side of the equation. We'll get that x is equal to -3. Okay? So x could be equal to -7/3, or it could also be equal to -3. Each of those would work as a solution to the original equation. In the interest of time, I'm not going to check it, but again, you can pause the video, go back to the original equation, plug in a -7/3 for each occurrence of x, and also a -3 for each occurrence of x, and verify that the left and the right sides are equal. All right, let's take a look at another. So we have -1 plus 7x is equal to -2x squared minus 4. So again, I want this in standard form. So ax squared plus bx plus c is equal to 0. Okay? It helps if you write it out and you can kind of look at it and see what you need to do. So I am going to basically follow this format and have 0 on the right-hand side. So I'm just going to add 2x squared to both sides of the equation. And I'm going to add 4 to both sides of the equation. So this is going to cancel. So the right-hand side is just going to be a 0. Okay? On the left-hand side, I'll have my 2x squared. And then you have 7x, so plus 7x. And you got -1 plus 4, which is going to be plus 3. And again, this is equal to 0. So now that I have it in standard form, I can go ahead and factor the left-hand side. And this guy, again, is pretty easy to factor because this part right here is a prime number. So I'll go ahead and set this up. We'll have our 2x and our x. So now I just need to work out this and this, right? Again, we want this times this plus this times this to give me this middle term, this 7x. So what are the factors of 3? Well, it's only 1 and 3, so it's not very hard here. You can either put plus 3 here and plus 1 here. That obviously doesn't work. You'd end up with 2x plus 3x, which is 5x. So it has to be true if it's factorable that a 3 would go here and a 1 would go here, and that does work, right? 2x times 3 is 6x, and then 1 times x is 1x. So this ends up being 7x, which is the correct middle term when you do that sum, okay? So we factor this guy, and now we're going to set it equal to 0. And again, we're just going to use our 0 product property. So this guy right here, we're going to set this equal to 0. Let's start with that. So 2x plus 1 is equal to 0. Let's subtract 1 away from each side of the equation. We will get that 2x is equal to -1. We will take this 2x is equal to -1 and divide both sides by 2. We'll get that x is equal to -1/2. Okay, so let's say x equals -1/2. And then the other solution comes from this guy on the right. So this factor here, this x plus 3, if I set that equal to 0, so x plus 3 equals 0, subtract 3 away from each side of the equation, you get x is equal to -3. Okay, so -3 goes here as well. So my two solutions here, we have that x equals -1/2, and then also x can be -3. All right, let's look at one that's not a quadratic equation. And the reason it's not a quadratic equation is because we have x raised to the third power here. So that would violate our definition. But it's important to know that you can use this technique for any equation if it's factorable, okay? So it doesn't have to be a quadratic equation. So we have x cubed minus 3x squared minus 4x plus 12 equals 0. And we know if we have a 4-term polynomial, we want to try to factor this using the grouping method. So from the first group, I can see that I can pull out an x squared. That would give me an x minus a 3. From this group here, to match this, I would pull out a -4, and that would give me an x minus a 3, and this equals 0. Of course, my common binomial factor here is the x minus 3, okay? So this ends up giving me my x minus 3, and then times the quantity x squared minus 4, and this equals 0. So at this point, we're not actually done factoring because the x squared minus 4 part is the difference of two squares. So we want to factor this all the way. So let's put x minus 3, and then times, this guy would factor into x plus 2 times x minus 2, and again, this equals 0. So all we're doing now is we're taking each factor and setting it equal to 0. So x minus 3 is equal to 0. We add 3 to each side of the equation. We get x is equal to 3. Okay, so that's one solution. So x is equal to 3. Another solution, we have x plus 2 is equal to 0. Subtract 2 away from each side of the equation. This cancels. You get x is equal to -2. So that's another solution. And then a lot of you can guess that the final solution is x equals 2. But for the sake of completeness, let's just do it. So x minus 2 equals 0. Add 2 to each side of the equation. And this cancels. You get x is equal to 2. So that's our last solution. So here, x can be 3, it can be -2, and it can be 2. In this lesson, we want to review the square root property. So in our last lesson, we reviewed how to solve a quadratic equation using factoring. Although factoring is the simplest method that we can use to solve a quadratic equation, it's not going to work in every scenario. So we need other tools that will basically work for every quadratic equation. And in this lesson, we're going to lay the groundwork for our methods known as completing the square and also the quadratic formula. So we're going to start out today by talking about the square root property. So essentially, if we have a variable like x and it's being squared and it's set equal to some number k, then we can solve this equation for x and say that x is equal to the square root of k or x is equal to the negative square root of k. So it's very important to understand why we have these two square roots here, right? The principal and the negative. So let's say we had something like x squared is equal to just the number 9. Well, if I want to solve this guy for x, again, we're always looking to undo what's being done to x. Here, x is being squared. So the opposite operation of squaring something is taking the square root. So I'm going to take the square root of each side of the equation. And if I don't go plus or minus here, I'm not going to get my full solution. We know that this index here of 2 will cancel with this exponent of 2. And I get that x is equal to, the principal square root of 9 is just 3. Now think about this for a minute. Did I get the correct full solution? If x squared is equal to 9, well, 3 squared is equal to 9, but also negative 3 squared is equal to 9. So in order to get the full solution here, I've got to have plus or minus the square root of 9. So this leads to x equals 3 or x equals negative 3. Again, 3 squared is 9, and also negative 3 squared is 9. So because of the squaring operation and the fact that it takes a negative and creates a positive, and also takes the positive and gives us a positive, we've got to include the plus or minus symbol when we take the square root over here on the right-hand side. Let's take a look at an example. So suppose we had x squared equals 121. So let me rewrite the problem over here. So we have x squared is equal to 121. Again, if I want to solve this guy for x, I would take the square root of this side. Let me kind of make that a little better. And I would go plus or minus the square root of this side. Okay? So we know that this guy right here is just going to be x. And this is equal to plus or minus. The square root of 121 is 11. So we get that x equals 11 or x equals negative 11. Okay? So you can leave it in this format. This is more compact. Or you can write it like this, x equals 11, comma, negative 11. Or you could use your or keyword. You could say that x equals 11 or x equals negative 11. Okay, all of these are kind of different ways to notate the same thing. But when you work with these equations, you don't need to go through and take the square root each time. You can just use your property, right? I could have started this by just saying, okay, I have x squared is equal to some number, let's just call it k. So this leads to x is equal to the square root of k, or x is equal to the negative square root of k. So if I have this format, I can say x is equal to the square root of 121, or x is equal to the negative square root of 121. Again, this would just lead to x is equal to 11 and negative 11. Okay, because the principal square root of 121 is 11. And again, the negative square root of 121 is negative 11. All right, let's look at another one. So we have x squared equals 54. So again, if I want to solve this for x, again, I can use my property. I can say that x is equal to plus or minus the square root of 54. Okay, so what is 54? It's not a perfect square. So we can break this down. 54 is basically 27 times 2. We know 27 is 9 times 3. 9 is a perfect square because it's 3 times 3. All right, so you have kind of those prime factors there. So I can say that x is going to be equal to plus or minus. The square root of 9 is 3, so go ahead and pull that out. You would have 3 times the square root of 3 times 2, which is 6. And essentially, you can leave your answer like that. That would be perfectly acceptable. Or, again, you could write it like this. You could say that x is equal to 3 times square root of 6, and then comma, negative 3 times square root of 6. All right, let's look at one that's a little bit more challenging. So we have 2x squared plus 10 is equal to 152. So how do I solve this for my variable x? Again, just like when we worked with any other type of equation, we want to start by getting the variable term with x involved isolated on one side. So how do I do that? I just want to subtract 10 away from each side of the equation. So I would have that 2x squared is equal to 152 minus 10 is 142. Now again, I want to get the x squared by itself. So I need to divide both sides of the equation by 2 so I can isolate the x squared part. So we know that this is going to cancel, and I'm going to have x squared is equal to 142 divided by 2 is 71. And now that I have it in the format of x squared equals a number, again, I can just use my property. I can say that x is going to be equal to the principal and negative square root of 71. Now 71 is going to be a prime number, so I can't really do anything else with this. This is just how I'm going to list my solution. Or again, I can say that x is equal to the square root of 71 and then comma the negative square root of 71. Again, any kind of way that you want to notate that. All right, let's look at another one. So we have 5x squared plus 9 is equal to negative 7. So again, I want to isolate x. And to start this off, I want to isolate the term with x involved. Okay, so I'm just going to subtract 9 away from each side of the equation. This is going to give me that 5x squared is equal to negative 7 minus 9 is negative 16. Again, now I want to isolate the x squared. So I'm going to divide both sides by 5. And this is going to give me that x squared is equal to, you've got negative 16 fifths. Okay, so now we have x squared equals some number. So now I'm going to use my square root property. Let me kind of divide this up. We're going to say that x is equal to plus or minus the square root of negative 16 fifths. Now there's a few things here. We have the square root of a negative, so we're going to use our imaginary unit I to kind of simplify this. So I'm going to say that x is equal to plus or minus. Again, we know how to use I at this point. This guy right here is just going to come out as I. So I'm going to put that right here. And then times, I'm going to break up the square root into the square root of 16 over the square root of 5. Okay? Now I can simplify this further because the square root of 16 is 4. So let me scroll down a little bit. So we're going to say that we have x is equal to plus or minus. Again, the square root of 16 is 4, so I'd have 4 times I. So 4i over the square root of 5. Now, we're not done yet because, again, we have to rationalize the denominator here. So I can do that pretty quickly. I would say the square root of 5 over the square root of 5 is what I need to multiply by. In the denominator, square root of 5 times square root of 5 is 5. So we'll just put x is equal to plus or minus. In my denominator, I have 5. In my numerator, I'm going to have 4i times square root of 5. Okay? So this is basically your answer. X equals positive or negative 4i times square root of 5 over 5. And again, you can break that up into two different solutions. You have 4i times square root of 5 over 5, or you have negative 4i times square root of 5 over 5. All right, let's take a look at another one. So suppose we had the quantity x minus 7 that's being squared, and it's equal to 64. Well, we can extend our property to this scenario as well. In fact, this is what we're going to end up doing when we use our completing the square method. So what I'm going to do, let me kind of show this the long way. So we have x minus 7, this quantity squared is equal to 64. I'm going to take the square root of this side. And we all know that what's going to happen is this 2 right here is going to cancel with this 2 right here. So on the left side, I'm just left with my x minus 7. But on the right side, when I take the square root, I've got to go plus or minus the square root of 64. Okay? So this equals the principal square root of 64 is 8, and the negative square root of 64 is negative 8. So you could say plus or minus 8 there. Now, we're not done. So in this particular case, I've got to kind of break this up and look at both solutions. So I've got to say that x minus 7 could be equal to positive 8, then or x minus 7 could be equal to negative 8. Okay? So I'm going to solve each equation here. So I add 7 to each side of the equation. I get x is equal to 15. Then or I add 7 to each side of the equation, and I get x is equal to -1. So let's erase everything. We're going to go back up, and I'm going to check these two solutions, and we're going to think about why they work. So again, we get that x equals 15 or x equals -1, and we can write that in a more compact manner by just saying x equals 15 comma -1 like that. Let's think about why these solutions work. If I started out with 15, then I would have 15 minus 7 inside of parentheses being squared, and this equals 64. Essentially what I'm saying is 15 minus 7 is 8. I'm saying that positive 8 squared is equal to 64. So another thing would be that I need -8 squared to give me 64 as well, and that's what -1 is going to give me. If I put -1 in there, what's going to happen is -1 minus 7 is -8, so -8 squared is also 64. So again, that's why you have those two solutions. You don't know whether it's 8 that's being squared that gives you 64, or whether it's -8 that's being squared that gives you 64. So that's why you've got to say that x minus 7 could be equal to the positive or the negative square root of 64. Okay, that's why you have to have those two scenarios to give you all of the possible solutions. All right, let's look at another one. So suppose we had the quantity 2x minus 1 squared is equal to 18. So same thing here. I'm going to take the square root of the left side, so the square root of this side, and again, we know that this 2 cancels with this 2. Then on the right, I've got to do the positive and negative square root of 18. Okay, so we know on the left that we're just going to have our 2x minus 1. This is equal to, on the right, if I think about 18, I know it's 9 times 2. 9 is a perfect square, it's 3 times 3. So I can pull that 9 out and say we have plus or minus 3 times the square root of what's left, which would be 2. Okay? So now I've got two different solutions that I've got to work out. I've got 2x minus 1 is equal to 3 times square root of 2, and then I've got 2x minus 1 is equal to the negative of 3 times square root of 2. So let's set those up and solve them individually. So I have 2x minus 1 is equal to 3 times square root of 2, or I've got that 2x minus 1 is equal to negative 3 times square root of 2. Okay, so let's solve these guys. So over here I've got where I can add 1 to each side of the equation, so that's going to cancel. I'll have 2x is equal to 3 times square root of 2 plus 1. If I want to solve for x, I just divide both sides by 2. And I'm going to get that x is equal to 3 times square root of 2 plus 1 over 2. And I really can't simplify that any further, so I just leave it in that format. So over here, if I add 1 to each side, this cancels. I'm going to have that 2x is equal to negative 3 times square root of 2 plus 1. Then what I can do is divide both sides of the equation by 2, and I get that x is equal to negative 3 times square root of 2 plus 1 over 2. So when we notate this, we can just put or between these two, because x could be 3 times square root of 2 plus 1 over 2, or x could be negative 3 times square root of 2 plus 1 over 2. The other method would be to use a shorthand. So I could say x is equal to plus or minus 3 times square root of 2 plus 1 over 2. Okay, so both of these ways to notate this would be acceptable. And I just want to show you real quick another way to do this. So let's erase all this. I'm going to show you kind of a faster method. So you don't need to split this up into two different equations. You can solve this without doing that. So from here, I can just add 1 to each side of the equation. I would say this is 2x is equal to plus or minus 3 times square root of 2 plus 1. So now if I want x by itself, I can just divide both sides by 2. And what do I get? I get that x is equal to plus or minus 3 times square root of 2 plus 1 all over 2. So this is a more compact form, and it's also a quicker way to get the solution, right? Again, x is equal to the positive or negative of 3 times square root of 2 plus 1 over 2. So it's two solutions. X is going to give me 3 times square root of 2 plus 1 over 2, and x is also going to give me the negative 3 times square root of 2 plus 1 over 2. All right, let's take a look at one more of these. And this problem is going to lead us into our next lesson where we talk about completing the square. So here we have 16x squared minus 56x plus 49 equals negative 27. How can I solve this for x? This currently doesn't look like x squared equals a number, or even kind of something like this where we have the quantity ax plus b squared is equal to some number k, right? We know how to solve this one, and we know how to solve this one. But we don't know how to solve this one yet. So essentially what I want to think about is the fact that the left side of this guy is a perfect square trinomial. When we have a perfect square trinomial, we can factor it into a binomial squared, okay? So think about the fact that you could factor the left side here into 4x minus 7, that quantity squared, okay? So if we set this equal to negative 27, now we have something that we can solve, right? So essentially what I'm going to do here is I'm just going to take the square root of this side, and I'm going to just kind of slide this down. I'm going to take the positive or negative square root of this side, okay? So we know that this cancels with this, and I have 4x minus 7 on the left, and this is equal to plus or minus the square root of negative 27. Now, to simplify here, I can pull this negative part out, and let's go ahead and say this is 4x minus 7 is equal to plus or minus. If I pull that out, I get I. If I think about 27, I know it's 9 times 3. 9 is a perfect square, right? So I can pull the square root of 9 out as 3. So I'll say this is the 3i right there, then times the square root of 3. All right, so now we can solve this guy for x. And again, we can do it in a quicker way by just not splitting this up. So I'm just going to add 7 to each side of the equation here. And I'll say this is 4x is equal to plus or minus. You've got your 3i times square root of 3 plus 7. And then to finish this up and to solve for x, I'm going to divide both sides of the equation by 4. And that's going to give me a final answer here of x is equal to plus or minus 3i times square root of 3 plus 7 all over 4, okay? So again, this is two solutions. We've got x equals 3i times square root of 3 plus 7 over 4. And then we've got x equals negative 3i times square root of 3 plus 7 over 4. In this lesson, we want to review solving quadratic equations by completing the square. So in our last lesson, we talked about the square root property. We said that if we had a variable like x that was squared, and it was set equal to some number, let's just call it k, then our solutions for this equation, we could say that x is equal to the principal square root of k, or x is equal to the negative square root of k. And we can abbreviate this and say that x is equal to plus or minus the square root of k. Remember, when you write it like this, this is two solutions. The principal square root of k, and then also the negative square root of k. And remember why we have to kind of set it up this way. If I had something like, let's say, x squared, and let's say this was equal to the number 16. Well, if I want to solve this for x, if I take the square root of this side to undo the squaring operation, well, then over here, I've got to put plus or minus the square root of 16. If I just took the principal square root of 16, I wouldn't get all the answers, okay? And if we go through and kind of cancel here, we know that this index would cancel with this exponent. That isolates x on the left side. On the right side, I have plus or minus the square root of 16, which is plus or minus 4. Now think about the fact that in the original equation, if I kind of erase all this, you had x squared equals 16. So 4 squared is 16, but also negative 4 squared is 16. So when you go through and you solve these things, make sure that on the side over here with your number part, you go plus or minus and then the square root of that, okay? That's going to give you all of your solutions. Again, in this case, you just get that x is equal to plus or minus the square root of 16 is 4. So let's look at two examples real quick, and then we'll go into completing the square. So x squared equals negative 36. So we have some variable x that's squared, and it's equal to some number negative 36. So using the square root property, I know that this would just be x is equal to the positive or negative square root of negative 36. Again, where does this come from? Well, if I have x squared equals negative 36, I can take the square root of this side so that I can get x by itself. But then over here, when I take the square root of this number, negative 36, I've got to go plus or minus the square root of that guy to get all my solutions. So that's how I get plus or minus the square root of negative 36. But of course, we can kind of simplify this. Let me erase this real fast. We can simplify this. We know that this guy right here, if I have a negative under a square root symbol, I can pull that out as I, okay? So I can say this is x is equal to plus or minus I times the square root of 36. The square root of 36 is 6, so I can say x is equal to plus or minus 6i. Now, you can check this if you want. Plug in a 6i for x and square it. Then plug in a negative 6i for x and square it. In each case, you will get negative 36. Now let's talk about this other scenario. This quantity x minus 5 squared equals 29. So this is what we want to focus on today, because this part right here is what we need to understand. We can also use the square root property there. So if I had the quantity x minus 5, and it's being squared, and it's equal to 29, well, what happens is I can take the square root of this side, and then we kind of slide this down. I can go plus or minus the square root of this side. It's the same thing. I'm taking the square root over here. I need the plus or the minus. So if I write this with a visible index of a 2, this cancels with this, and I'm left with just the x minus 5. That's what was being squared. And this equals plus or minus the square root of 29. Okay? So I'm going to split this up into two different equations. So I would have that x minus 5 is equal to the square root of 29. Then or x minus 5 is equal to the negative square root of 29. Now, if you wanted to, you could also solve this just kind of by doing this. You can add 5 to each side of the equation there. That's fine too in this particular case, because you can't simplify the square root of 29. But for right now, I'm just going to do this the long way. So over here, I'm going to add 5 to each side of the equation. How we get that x is equal to, I'll just put my 5 in the front, and then plus the square root of 29. And then or, over here, I'm going to add 5 to each side of the equation. I'm going to say x is equal to 5 minus the square root of 29. So obviously, if you kind of look at it this way, you can say, okay, the only difference between this is the positive or principal square root of 29, and this one's the negative square root of 29. So you can say this is x equals 5 plus or minus the square root of 29. This is the most compact way to write it. This is also correct. Or again, you could write x equals 5 plus the square root of 29, comma, x equals 5 minus the square root of 29. Any way you want to notate it, it's all the same thing. All right, so let's talk a little bit about completing the square. If you've never done this before, the process is very tedious, and you end up working with a lot of fractions, and just a lot of people really don't like completing the square. It's not that it's hard. It's just a lot of like kind of scratch work that you have to do. So it's something you do need to understand, but in the next lesson when we talk about the quadratic formula, you'll be able to solve any quadratic equation that you want without much effort. Okay, so this is just something you need to understand for your kind of future in math. So completing the square. So the first two steps can kind of go back and forth based on the situation you're in, and I'll explain that as we get into the examples. So the first step is to make sure the squared term has a coefficient of 1. So if I had something like, let's say 6x squared plus, let's say x minus 2 equals 0. In this particular case, I don't have a coefficient of 1 on the squared variable. Okay, I have a 6. So what can I do? Remember, I can multiply or divide both sides of the equation by the same non-zero number and not change the solution. So I can legally divide both sides of the equation by 6, and I can transform this into x squared plus, you could say 1/6x, and then 2 over 6 is 1/3, so minus 1/3 is equal to 0. Okay, so in some cases you'll do that first, in other cases you'll do it second. All right, so the second step, or in some cases it could be the first, you're going to move all variable terms to one side and the constant to the other. So let's say I had something like x squared plus 3x minus 7 equals 0. What I want is I want this part right here on one side by itself, and I want the number on the other side. So I would just add 7 to both sides of the equation, okay? That way over here, I would say this is equal to 7, all right? Now this part right here is where it gets a little bit confusing, and we'll look at this in the example. So we're going to multiply the coefficient of the x to the first power term by 1/2, then square. And some people say divide by 2. If you divide by 2 or you multiply by 1/2, it's the same thing, okay? So however you want to remember that. But remember, you're going to take it and you're going to cut it in half and then square it, Okay, and we'll see that in a minute when we look at an example. All right, then we're going to add the result to both sides of the equation. This will create a perfect square trinomial on one side of the equation. So a perfect square trinomial on one side of the equation. So in case you forgot, a perfect square trinomial is a trinomial that we can factor into a binomial squared. So something like x squared plus 2xy plus y squared. We previously learned in special factoring that this factors into the quantity x plus y squared. We want to put it in this format so that we can use our square root property, okay? Here I have that we're going to factor the perfect square trinomial into a binomial squared, okay? And then you're just going to solve the equation using the square root property. So it's a lot of steps that I gave you. You probably want to go back and just write all the steps down, and we're just going to look at a lot of examples, and this is one thing that you just have to practice, and after you get enough practice on it, it becomes very, very easy. All right, let's go ahead and look at the first example. This one's very, very easy. I kind of set everything up for you already. So we have x squared minus 13x equals 14. Okay, so the first two steps that I gave you, one of them was to make sure that the coefficient on the squared variable is a 1. You already have that in this case. This is a 1. The second step is to move all the variable terms to one side and all the numbers to the other. Here you have a variable term x squared and a variable term negative 13x on one side, and you have a constant 14 on the other. So you don't need to do any of the first two steps here. They're already done for you, okay? So we're going to move into the more complicated step, which is to basically complete the square. So again, what am I trying to do here? I'm trying to make the left side, this x squared minus 13x, into a perfect square trinomial. So I want something that will factor into a binomial squared. That's going to allow me to use my square root property and get a solution for x. So how can we do that? Again, we want to look at the coefficient for the x to the first power. We want to cut it in half, and then we want to square it. So if I took negative 13 and I multiplied it by a half, and then I squared that, what would I get? You would get negative 13 halves squared. Negative 13 squared is 169. 2 squared is 4. Okay, so I'm going to add this value to the left-hand side, but to make it legal, I've also got to add it to the right-hand side. So let's go ahead and set that up. So on the left, my equation will become x squared minus 13x plus 169 fourths is equal to, again, to make it legal, I've got to do it to the right side, so 14 plus 169 fourths. Okay, so let's scroll down and get some room going. All right, so the first thing I'm going to do now is just factor the left side of this. So this is going to factor into x minus 13 halves, that quantity squared, okay? Then this equals, here comes a part that's pretty tedious. You've got to simplify over here, and you need to get a common denominator. So sometimes this can take a little bit of time. Again, that's why students don't like this method, because it's just very, very tedious. So let me kind of move this down. So plus 169 fourths. I'm going to multiply this by 4 over 4 so I can have a common denominator. 14 times 4 is 56. And if I added 56 and 169, I get 225. So this right side here would be 225 fourths. Okay, so let's put 225 fourths. And now I have it into a format where I can solve using the square root property. You've got something over here that's squared. This quantity x minus 13 halves, that's squared, and it's just equal to some number. Well, just like we did earlier in the lesson, if I take the square root of this side, remember this has an index of 2 here, this cancels with this, and I've got x minus 13 halves. But again, you got to remember this number here on the right, I've got to go plus or minus the square root of this, okay? So this equals, you've got your plus or minus. You can split this up legally. So you can say the square root of 225, which is 15, over the square root of 4, which is 2, okay? So I've got my two different equations to work on. You're going to have x minus 13 halves is equal to 15 halves, and you've got x minus 13 halves is equal to negative 15 halves, okay? So let's set those up. So x minus 13 halves is equal to 15 halves, and you can do or x minus 13 halves is equal to negative 15 halves, okay? So let's solve these guys and we'll have our solution. Okay, so all I'm going to do here is just add 13 halves to each side of the equation. That's going to give me that x is equal to 15 plus 13 would be 28. 28 over 2 is 14. Okay, so that's one solution. My other solution, if I add 13 halves to both sides of the equation, what am I going to get? Well, negative 15 plus 13 is negative 2. Negative 2 over 2 is negative 1. So then x would be equal to negative 1. So there's your two solutions. You get that x equals 14 or x equals negative 1. You could leave it like this. Of course, you could write it as x equals 14 comma negative 1. Again, many different ways to kind of notate this. All right, let's kind of turn the heat up just a little bit and look at one that's a little bit harder. So we have x squared plus 18x plus 85 equals 0. So I still have a coefficient on x squared of 1, so I can kind of skip that step. But in this particular case, I have this constant term on the left-hand side, right? I'm adding 85. So I want to get rid of that before I do anything else. So I'm just going to subtract 85 away from each side of the equation. Again, you want all the variable terms on one side, all the numbers on the other. So I'm going to get x squared plus 18x is equal to negative 85. Let me kind of move this down. All right, so I want to complete the square on the left-hand side. Again, I'm trying to get a perfect square trinomial over here. I want this to end up being a binomial squared, okay? So how can I do that? Again, all I want to do is look at the coefficient of x to the first power. In this case, it's 18. So what is 1/2 of 18 squared? Again, take 18, multiply it by half, or as I say, cut it in half, and then square it. 18 times a half, or 18 divided by 2 is 9. 9 squared is 81. So this is what I need to add to both sides of the equation to complete the square. So let me kind of make some room here. So I add 81 on the left side. That completes my square. This equals, to make it legal, I've got to add 81 on the right side. Okay. On the left, I can factor this now as x plus 9, that quantity squared. On the right, negative 85 plus 81 is negative 4. Okay. So now I can solve this using my square root property. So I can take the square root of this side, and then again, you've got to do plus or minus the square root of this side, okay? So this quantity here, x plus 9, is what we're going to have on the left. And this equals plus or minus the square root of negative 4. We know that the square root of negative 4 could be written as 2i. So let's go ahead and write this as x plus 9 is equal to plus or minus 2i. Okay. Nice and easy from here. I'm just going to go ahead and solve the two equations that I would get. So let's set this up and say that x plus 9 is equal to 2i, or x plus 9 is equal to negative 2i, okay? Now, in this particular case, because you really can't do anything, and you'll see what I mean by that, you really can't do anything once you subtract 9 away from each side of the equation. You can kind of just write it in a compact form. So let me do it as or, and then I'll kind of bring it back together. So I'm going to subtract 9 away from each side. I'm going to say x is equal to, I'm going to write my negative 9 first, and then plus my 2i. Then or, over here I'm going to subtract 9 away from each side of the equation. So x is equal to, again, negative 9, now minus 2i. So the only difference between these two solutions is the plus here and the minus here. So when this happens, you can use that more compact form. That's typically what you're going to see. So you can just say that x is equal to negative 9, which is the same in each case, then plus or minus the 2i. Okay, this is just more convenient to do it that way. But this is fine too. If you want to notate it this way, perfectly valid. They say the same thing. They mean the same thing. Don't get caught up on the notation. All right, let's look at a harder example. So we have negative 105 plus 23x equals negative 10 minus 6x squared. So in this particular case, you kind of have a mess, right? You have terms all over the place. You definitely are not going to have a 1 as the coefficient for x squared. So if you get something that looks like this, the first thing you need to do is clean it up. So what I would say is go to your second step first, which is to put all the variable terms on one side, all the numbers on the other. So what I'm going to do, I like my variables to be on the left. I'm going to add 6x squared to both sides of the equation. And that's going to cancel this over here. Then what I'm going to do is I'm going to add 105 to each side of the equation. And that's going to cancel that over there. So on the left, I'm going to have my 6x squared plus my 23x, and this is equal to, on the right, negative 10 plus 105 is 95. So from here, I have all the variable terms on one side and a number on the other. Don't forget to make this coefficient into 1. If you don't do that, you're not going to get the right answer. A lot of students, they kind of set this up, and then they start the process, and they go, okay, 23, cut it in half, and square it. No, okay, don't do that. You need to make sure that this coefficient here is a 1. So divide both sides of the equation by 6. Again, that's legal. So this cancels with this. I now have x squared plus I have 23/6 times x, and this is equal to 95 over 6, okay? All right, so what do I want to do now? I'm going to complete the square on the left side. So that 23/6 that I'm working with, I want to cut that in half. So multiply it by a half, square the result, okay? So you're going to end up with 23/12. You're going to square that. We know that 12 squared is 144. That's easy. But does anybody know what 23 squared is? Well, it happens to be 529, okay? So this is the value here that you're going to add to both sides of the equation so that on the left side you end up with a perfect square trinomial. So on the left, I've got my x squared plus my 23 over 6 times x plus my 529 over 144. And this equals, on the right, I'm going to have 95 over 6. And then let me kind of just drag this down. So it's going to be plus this value, okay? And I'll scooch it out so I can have room for my common denominator. All right, so on the left side, I can factor this into a binomial squared. So this is x plus, this guy is going to be 23/12. And this is squared, and it's going to be equal to, over here, to get a common denominator, I need to multiply this by 144 divided by 6 is 24. So this would be multiplied by 24 over 24. So 95 times 24 is 2,280. And then 2,280 plus 529 is 2,809. So this would be 2,809 over 144. Again, this is why students don't like completing the square, because you end up with just kind of a big mess like this. These are kind of larger numbers to work with. I know you can use a calculator, but still. When you see the quadratic formula, you'll see how much easier that is. All right, so we can solve this using our square root property. Square root of this side plus or minus the square root of this side. Again, don't forget this. So over here I have x plus 23/12 is equal to, you've got plus or minus, the square root of 2,809 is 53. Square root of 144 is 12. Okay, so let's scroll down and get some room going. So you're going to have that x plus 23/12 is equal to 53/12. Or, let me kind of make that 2 a little bit better. You'll have that x plus 23/12 is equal to negative 53/12. Okay, let me make that equal sign a little better. Okay, so let me scroll down and get some room going so we can see what's going on. On the left equation here, let's subtract 23/12 away from each side of the equation. So that cancels. You've got x is equal to 53 minus 23 is 30. So you'd have 30 over 12. 30 is divisible by 6, and so is 12. 30 divided by 6 is 5. 12 divided by 6 is 2. So 5 halves would be one solution for x. Another solution, if I go over here, if I subtract 23/12 away from each side of the equation, then this cancels. You're going to get that x is equal to, I have negative 53 minus another 23. That would give me negative 76. So let me write this down here. And I'm just going to put or instead of the comma. So x equals, you've got negative 76 over 12. I know that 76 divided by 4 is 19. So I could write this as negative 19, and 12 divided by 4 is 3. So I have two solutions, x equals 5 halves, or x equals negative 19 thirds. All right, let's take a look at another one. So we have 4x squared plus 8 equals negative 1 plus 2x squared minus 7x. Again, if it's a mess like this, go ahead and do the second step first. Clean everything up, put all the variable terms on one side, all the numbers on the other. You can see that you have like terms here and here, so they're on two different sides of the equation, so you got to clean that up first before you can really do anything. So let's subtract 2x squared away from each side. And let's subtract 8 away from each side. And let's add 7x to each side, okay? So that canceled and that canceled. And on the left, I'm going to have negative 2x squared plus 4x squared, which is 2x squared. And then plus 7x is equal to negative 1 minus 8 is negative 9. Okay, So from here, I can now think about the coefficient of x squared. We've got to make that a 1. Let's scroll down. And I'm going to divide each side by 2. Okay? Make sure you do this step. Again, it's very crucial. So you have your x squared plus your 7 halves x is equal to negative 9 halves. Okay, so now I want to complete the square on the left-hand side. So what do I want to do? I want to take 7 halves, the coefficient for x to the first power, and I want to cut it in half, meaning I'm going to multiply by half or divide by 2, whatever you want to do, and then square it. Okay, so 7 halves times a half, square it. 7 halves times a half is 7 fourths. If I squared that, I would get 49 sixteenths. Okay, so that's what I need to add to both sides of the equation. So on the right side, let me just give myself some room. So 49 sixteenths. On the left side, let me kind of scooch this down just a little bit. So plus 49 sixteenths. Okay, so at this point, you could probably do this in your sleep. Factor the left-hand side, it's x plus 7 fourths squared. On the right side, I've got to get a common denominator, so multiply this by 8 over 8. We know negative 9 times 8 is negative 72. If I add that to 49, I get negative 23. So this is negative 23 sixteenths. So I can solve this with my square root property. So square root of this side plus or minus square root of this side. Kind of scroll down here. So here I'm going to have x plus 7 fourths is equal to plus or minus. Pull this negative out and just say this is I. Then times, I'm going to do the square root of 23. And this is over, square root of 16 would be 4. Okay. Now you can't do a whole lot to simplify this. So I'm going to kind of do a quicker method. I'm just going to subtract 7 fourths away from each side of the equation. And I'm going to write this as x is equal to, I'm going to put negative 7 plus or minus I times square root of 23 over the common denominator of 4. Okay. Notice if you had negative 7 fourths and then plus or minus this whole thing here, you'd have a common denominator of 4. Okay. So that's why I wrote it like this. You can break it up if you want. You can say x is equal to negative 7 over 4 plus or minus I times square root of 23 over 4. Okay, you can do it that way as well. It's two different solutions either way. It's negative 7 plus I times square root of 23 over 4 and negative 7 minus I times square root of 23 over 4. Over here, it's negative 7 fourths plus I times square root of 23 over 4 and negative 7 fourths minus I times square root of 23 over 4. So however you want to notate it, again, I get a lot of questions about notation. This is the same as this. It does not matter. Okay, please don't get tripped up on something that's very, very inconsequential. Okay, doesn't matter. All right, let's look at one more of these, and I think we'll pretty much have it. So again, we have a situation where it's pretty messy. I mean, it's not as messy as the other ones, but I have a 9x squared here on the left and a 4x squared here on the right. So I want to clean that up first. So let me just move all the variable terms to one side, all the numbers to the other as the first step, and then we'll get the coefficient of x squared to be a 1 in the second step. So for this one, I'm going to subtract 4x squared away from each side of the equation. I'll have 5x squared minus 6x. Subtract 23 away from each side of the equation. So this is going to be equal to negative 23. So again, in order to complete the square, this coefficient has to be a 1. So we can divide both sides of the equation by 5 to accomplish that. So I'll have that x squared minus 6/5 x is equal to negative 23 fifths. Okay, let me make that a little better. Let's scroll down and get some room going. So now I want to complete the square on the left. So again, I want to take this guy right here, the coefficient for x to the first power. I want to cut it in half. So just multiply by half and then square it. Okay, so negative 6/5 times a half is going to be negative 6/10. So negative 6/10 squared, this is going to be what? It's going to be 36 over 100. So on this side, I'm going to add 36 over 100. On this side, I'm going to add 36 over 100. Okay? So from this point, it's pretty easy. On the left side, I'm going to factor this. Don't forget that you have a minus there. So this is x minus. You're going to have 6/10 here, and then this is squared. And this equals, on this side, I need a common denominator. So let me kind of slide this down. So negative 23 fifths times, to get a denominator of 100, I need to multiply by 20 over 20, okay? So negative 23 times 20 is negative 460. If I added 36 to that, I would get negative 424. So equals negative 424 over 100. Now, if you want to, you can make this simpler at this point. I know that each is divisible by 2. I also know that each is divisible by 4, right? Because 424, forget about the fact that it's negative. It doesn't affect divisibility. The 24 there tells me that it's divisible by 4. So 424 divided by 4 is going to give me 106. So go ahead and write this as negative 106. And then 100 divided by 4 is 25. Now 25 is 5 times 5. 106 is not divisible by 5, so there's nothing else you can do there. So what I'm going to do is solve this with my square root property. Plus or minus square root over here. So I've got x minus 6/10 on the left, and this equals, let me get some room. So I've got plus or minus the square root of negative 106 over square root of 25 is 5. So I know that I can pull out the negative part as I. So let's go ahead and write x minus 6/10 is equal to plus or minus I times the square root of 106, and this is over 5. All right, so to solve this, I'm going to add 6/10 to each side of the equation. I'm going to get that x is equal to, I'm going to have 6/10, and then plus or minus I times the square root of 106 over 5. Now, I want you to realize that 6 over 10 can be reduced. 6 is 3 times 2, 10 is 5 times 2. So if I divide this by 2, I get 3. If I divide this by 2, I get 5. So now I have a common denominator. So I can write this as x is equal to, I'll have 3 plus or minus I times the square root of 106 over that common denominator of 5. Again, this is two solutions. You've got x equals 3 plus I times the square root of 106 over 5, and x equals 3 minus I times the square root of 106 over 5. In this lesson, we want to review solving quadratic equations using the quadratic formula. So in our last lesson, we reviewed how to solve any quadratic equation by completing the square. Now, most students hate this method because it's just so tedious. So fortunately for us, there's an easier method known as the quadratic formula. So this basically allows us to take any quadratic equation, which is written in standard form, and just plug in the values for a, the coefficient of x squared, b, the coefficient of x to the first power, and c, the constant, and immediately obtain a solution. So first and foremost, the quadratic formula is derived from taking this ax squared plus bx plus c equals 0 and essentially just solving it for x by completing the square. So I'm going to go ahead and show you that process just so you know where this is coming from. And then from here on out, we can just use the quadratic formula. It's very, very easy. So the first thing I want to do if I was completing the square on this, forget about the fact that you have no numbers involved other than 0. You have a that's the coefficient of x squared. We want to make sure this is a 1. So to ensure that, we're just going to divide each side of the equation by a. So that's kind of your first step. So we know that this cancels with this, and we would have that x squared plus b over a times x plus c over a is equal to 0. Now the next thing is to make sure that all the variable terms are on one side and all the numbers are on the other. So what I'm going to do is I'm going to subtract c over a away from each side of the equation, and that's going to give me that x squared plus b over a times x is equal to negative c over a. All right, so now I'm at the step where I want to complete the square. So essentially I want to transform the left side into a perfect square trinomial. So I want to take the coefficient of x to the first power, which in this case is b over a, and I want to cut it in half. So that means I want to multiply it by a half, and then I want to square the result. So this just becomes b over 2a, that amount squared. So this becomes b squared over 2 squared is 4, and then a squared is just a squared. Okay, so we're going to add this right here to both sides of the equation. So let me erase all this. We're going to have that x squared plus b over a times x plus b squared over 4a squared is equal to negative c over a. Again, plus this quantity. So plus your b squared over 4a squared. All right, so let's factor the left side as x plus, remember we squared b to get b squared, so this is b over. we square 2a to get 4a squared. So 2a, and this whole thing is squared, and this equals, if I get a common denominator going over here, I would need to multiply this negative c over a by 4a over 4a, okay? So that would give me b squared minus 4ac over the common denominator of 4a squared, okay? So now I can use my square root property, and I can take the square root of this side, and then plus or minus the square root of this side. So let's get some room going. So that would give me x plus b over 2a is equal to plus or minus the square root of b squared minus 4ac. If I take the square root of 4a squared, I just get 2a. Okay, so that's going to be my denominator. So if I want to solve for x, all I've got to do is subtract b over 2a away from each side of the equation. And notice how you have a common denominator here. So I can say that x is equal to, I'm just going to put the negative b out in front, then plus or minus my square root of b squared minus 4ac. This is going to be over the common denominator of 2a. So this is the quadratic formula. This is what we can use to solve any quadratic equation. So if it's in the format of ax squared plus bx plus c equals 0, I just record the values for a, b, and c, and I plug them in. So I'm going to plug in here for b and here for b. I'm going to plug in here for a and here for a, and I'm going to plug in here for c. Okay, so that's all I've got to do. So let me erase this, and we'll take this down to the next page, and we'll see an example. So let me paste our quadratic formula here. So this is what we're going to use to get our solution. So the very first thing you need to do is you need to make sure this is in standard form. It's not in standard form because you have 14x squared over here and 10x squared over here. You want ax squared plus bx plus c is equal to 0. So let's move this down for 1 second. I'm just going to subtract 10x squared away from each side of the equation. And this would cancel and give me 0. So essentially what I'd have is 14x squared minus 10x squared is 4x squared. And then minus 5x, and then plus 1 equals 0. All right, so let me erase this. All I need to do, I don't need to do anything fancy with this equation. I just need to record the values for a, b, and c. So a is the coefficient of x squared. So a here is going to be 4. b is the coefficient for x to the first power. So here that's negative 5. And c here is my constant term. In this case, this is 1. I want to caution you against something. You need to make sure this is in this format before you record the values, okay? If your equation is all jumbled up, like it is here, you're not going to get the right answer, okay? So make sure you put it in standard form first before you start this process. So now that I have the values for a, b, and c, I can just plug into my quadratic formula, and I'll have my solution. So x equals, you've got negative b. b is negative 5, so the negative of negative 5 is 5. Then plus or minus the square root of b squared. Negative 5 squared is 25. Then minus 4 times, for a we have 4, and then for c we have 1. Then this is over. 2 times a is 4 in this case. So 2 times 4 would give me 8. So now I just simplify this and I have my answers. So x equals 5 plus or minus 25 minus, basically 4 times 4 times 1 is 16. So 25 minus 16 is 9. So you'd have 5 plus or minus the square root of 9. We know the square root of 9 is 3, so just go ahead and write that as 3. And then this is over 8. So we can go ahead and say that we have x is equal to 5 plus 3 is 8, so you'd have 8 over 8, which is 1. And then 5 minus 3 is 2. 2 over 8 is 1/4, so you'd have 1/4 there as well. Okay? So just make sure you break that up and do both solutions, especially in this case because you want to say you have 5 plus 3 over 8. So that's one solution for x, and this leads to 8 over 8, which is going to give us 1. Okay, so that's how we got this guy right here. Then the other scenario is 5 minus 3 over 8. So that gives us 2 over 8, which is 1/4. So that's how we got this guy right here. So x basically is going to be equal to 1 or 1/4. Okay? And look how much quicker that was versus completing the square, or even if we were to use factoring, okay? Using the quadratic formula is generally the fastest method. All right, for the next one, we're going to look at -5 minus 2x equals -x squared. Again, I always want it in the format of ax squared plus bx plus c equals 0. So I'm going to add x squared to both sides of the equation. And I get x squared minus 2x minus 5 is equal to 0. So now all I need to do is record the values for a, b, and c and plug into the quadratic formula. That's all I need to do. So for a here, it's the coefficient of x squared. It's just going to be 1. So a is 1. B is what? It's the coefficient for x, so it's a -2. And c is going to be a -5, right? It's the constant. Okay, so let's erase this, and let's just kind of drag this up a little bit. And in case you forgot the quadratic formula, you can just keep writing it. You'll remember it pretty quickly. So it's x is equal to, you've got -b plus or minus the square root of b squared minus 4ac all over 2a. So I'm going to plug in for b. I've got a -2. So I'd have the negative of -2, which is +2. So x equals, you'll have 2 plus or minus the square root of b squared. You'd have -2 squared, which is 4, then minus 4 times a times c. A is 1, c is -5. So you'd have -4 times 1, which is -4, then times -5, which is +20. So we'll put +20 here. Let's get some room going. Then I have it over 2a. A is 1, so this is just all over 2. So this is just all over 2. So x is equal to, you've got 2 plus or minus, 4 plus 20 is 24. So the square root of 24, which we know we could simplify into what? Square root of 24 is the square root of 4, which is 2, times square root of 6. So this is 2 times square root of 6, and then over 2. Now, you could leave it like this, but you want to always simplify if you can. You want to think about the fact that you have a 2 here, a 2 here, and a 2 here. So really what I could say is it's x is equal to, factor out the 2 from the numerator, you would have 1 plus or minus the square root of 6 over 2. This guy would cancel with this guy, and I would have that x is equal to 1 plus or minus the square root of 6. And again, this is two different solutions. This is x equals 1 plus the square root of 6, and also x equals 1 minus the square root of 6. All right, let's look at another one. So we have 7 minus 5x is equal to, we've got -4x minus 3x squared. So again, clean this up, put it in standard form. You want your ax squared plus your bx plus your c is equal to 0. So what I'm going to do is I'm going to add 3x squared to both sides of the equation. And I'm going to add 4x to each side of the equation. And that's going to give me what? These cancel. This is 0 on the right. So I would have 3x squared. And then 4x minus 5x is -x. And then you'll have your +7. Okay, so this is equal to 0. So now all I need to do is record my values for a, b, and c. And I'm basically set, right? So a here is going to be 3. A here is 3. B here is -1. Okay, B here is -1. And C here is going to be 7. So I plug into my quadratic formula. So x equals -b plus or minus the square root of b squared minus 4ac all over 2a. Just keep writing it, and it's going to become second nature for you. You'll remember it in your sleep. So I'm going to go ahead and say that x is equal to the negative of b. B here is -1, so the negative of -1 is 1, plus or minus the square root of, again, b is -1, so b squared is 1. So you'll have 1 minus 4 times a. A is 3 here, so 4 times 3 is 12, times c. C is 7, and 12 times 7 is 84. So you'd have 1 minus 84, which is -83. And this is all over 2 times a. A in this case is 3, so 2 times 3 is 6. All right, so let me erase all this. We'll kind of look at these two different solutions here and see what we can do. So we know we would have x equals 1 plus the square root of -83 over 6, and then x equals 1 minus the square root of -83 over 6. What I can do to simplify here is say that x is equal to 1 plus or minus, pull out the negative part and say this is I, times the square root of 83 over 6. All right, let's talk a little bit about the discriminant. So the discriminant is basically the b squared minus 4ac It's the part of the quadratic formula that's underneath the square root symbol. So essentially, by looking at the discriminant, we can get a lot of information. We'll know the type of solution we're going to get, whether it's real or imaginary, and we'll also know the number of solutions we're going to get. So in the case where b squared minus 4ac is greater than 0, we're going to have two real solutions. Now, if this guy right here happens to be a perfect square, then you're going to get two rational solutions. Now, if b squared minus 4ac is equal to 0, then you're going to get exactly one rational solution. And the reason for that is the plus or minus the square root of b squared minus 4ac, if this guy is 0, you have plus or minus 0, which is just 0. Okay, so it kind of renders the plus or minus part ineffective. So if b squared minus 4ac is equal to 0, then you're just going to have one rational solution. So then the last kind of case is that b squared minus 4ac is less than 0. So in this case, you're going to have two complex solutions. All right, let's take a look at another one. So we have 10x squared plus x plus 1 equals 2x. I just want to subtract 2x away from each side of the equation, just to put this in standard form. So I'm going to have 10x squared. X minus 2x is negative x, and then plus 1 equals 0. So again, I want to record my values for a, which is 10 in this case, b, which is negative 1, and c, which is positive 1. So let's think about the quadratic formula. So x equals, you've got negative b. In this case, b is negative 1. So the negative of negative 1 plus or minus the square root of b squared, which is negative 1 squared, minus 4 times a is 10, times c in this case is 1. Okay, now this guy is going to be over 2 times a. So 2 times, in this case, a is 10. Now, what is this part right here? Again, the discriminant, this will predict the number of solutions and the type of solutions we're going to have. So negative 1 squared is 1, and then minus 4 times 10 is 40, times 1 is still 40. So you'd have 1 minus 40, which is negative 39. So if this is negative 39, I know that I'm going to have two complex solutions, okay? So let's go through this. The negative of negative 1 is just 1. And then if I think about plus or minus the square root of negative 39, 39 is 13 times 3, so there's nothing I can really do other than to pull this negative out. So I can put this as I times square root of 39, and then 2 times 10 is just 20. So essentially you can leave your solution in this format. This is perfectly fine. Or you could write that x is equal to 1 plus I times square root of 39 over 20, and then also x is equal to 1 minus I times square root of 39 over 20. All right, let's look at one more. So we have 8x squared minus 4 is equal to negative 8x plus 12x squared. So again, clean this up, put it in the format of ax squared plus bx plus c equals 0. So I'm just going to subtract 12x squared away from each side of the equation. And I'm going to add 8x to both sides of the equation. So this is going to cancel and become 0. I'm going to have that 8x squared minus 12x squared, which is negative 4x squared. And then we have plus 8x, and then minus 4 is equal to 0. A little trick to make this simpler. Whenever you work with stuff and you see that this is divisible by 4, this is divisible by 4, this is divisible by 4, and 0 is divisible by 4, I can just divide both sides of the equation by 4 and make this easier. I can also divide both sides of the equation by negative 4 if I want. It does not change the solution. Okay, it just makes it easier to work with. So this becomes x squared, this becomes negative 2x, this becomes plus 1, and this equals 0. Notice how I'm going to be working with smaller values for a, b, and c. It's just something you can do very quickly to make your life a lot easier. So let's go ahead and erase all this. Let's drag this up. And again, let's record the values for a, which in this case is a 1, for b, which in this case is negative 2, and for c, which in this case is 1. So we get x is equal to negative b, in this case b is negative 2, so the negative of negative 2, plus or minus the square root of b squared. So you're going to have negative 2 squared minus 4 times a, which is 1, times c, which is 1. Okay, this is all over. 2 times a is 1, so 2 times 1. Okay, so let's think about our discriminant and predict our solutions. So we have negative 2 squared, which is 4, okay? And then we're going to subtract away 4 times 1 times 1, which is 4. 4 minus 4 is 0. So this is going to be taking the square root of 0, which is 0. So since the discriminant is 0, I know I'm going to have one rational solution, right? Because you can basically get rid of this part here, and you can say that the negative of negative 2 is 2, and 2 over 2 would just be 1, so x here would just be 1. Okay, that would be your only solution. In this lesson, we want to review solving equations that are quadratic in form. So in some cases, we're going to come across an equation that is not a quadratic equation, but can be made into a quadratic equation with a simple substitution. So these equations are known as quadratic in form, and we can solve them using the same methods we used when we worked with quadratic equations. So we can use completing the square, we can use the quadratic formula. In some cases, we can use factoring. So let's take a look at the first example. So we have x to the 4th power minus 25x squared plus 144 is equal to 0. So I want you to notice here how the smaller exponent on x is a 2 and the larger exponent on x is a 4. Generally, when we work with a quadratic equation, you have ax squared plus bx, and I'm just going to say bx to the 1st power, plus c is equal to 0. So notice how this guy right here, this larger exponent, is double that of the smaller. It's the same thing here. The larger exponent is double that of the smaller, or you could say the smaller exponent is half of the larger, okay? So we see that pattern, and we also see that we have a constant here, and we have a constant here. So we can say that this equation is quadratic in form. So what we can do is make a little substitution, okay? So we're going to grab our variable that's raised to the smaller power, and we're going to set that equal to some other variable. It could be q, it could be z. A lot of people like to use u, okay? So I'm going to stick with that. I'm going to say, let's let our variable u be equal to x squared. Now, in order to do the substitution, and in order to show it to you, I'm going to use my rules of exponents, and I'm just going to rewrite my equation. So x to the 4th power, I'm going to write that as x squared being squared. Okay, I haven't done anything illegal. Power to power rule, that would still be x to the 4th power. Then minus 25x squared, then plus 144 equals 0. Let me make that 1 a little better. So everywhere I see an x squared, I'm just going to plug in a u. Okay, because u is equal to x squared. All right, let me get a little room going here. What I'm going to say is that I have u that's being squared. Again, just plugged in a u there. Then minus 25u. I'm plugging in a u there. It's not squared because I'm plugging in a u for the x squared. Okay, then plus 144 is equal to 0. Now, if I saw this initially, I would have a quadratic equation, and I could solve that either by completing the square or the quadratic formula, or again, in some cases with factoring. So let's go ahead and solve this using the quadratic formula, because I think that's usually the easiest scenario. So let's go ahead and put this as a visible 1 here. I'm going to say that my a, my coefficient for u squared in this case, normally it's x, but here it's u squared, is a 1. B, the coefficient for u to the 1st power, is a negative 25. And C, my constant, is 144. So A is 1, B is negative 25, and C is 144. Okay, so let's plug into the quadratic formula. So we would have that u is equal to, you've got the negative of b plus or minus the square root of b squared minus 4ac, and the whole thing is over 2a. So let's go through and just replace. So you've got the negative of b is negative 25. The negative of negative 25 is 25. Plus or minus the square root of, you've got b squared. Negative 25 squared is positive 625. So 625. Then minus, you've got 4 times a times c. A is 1, so we can just get rid of it. You can put times 1 if you want, but it's not going to change anything. And then c is 144. So c is 144. So what is 4 times 144? Well, that's 576. So 576. What is 625 minus 576? Well, that's going to give us 49. So we got a 49 here. And of course, if we took the square root of 49, we would get 7. So let's go ahead and put a 7 there. Now, we have 2 times a in the denominator. A is 1. So we basically just have 2. So what we have here is that u is equal to, you've got 25 plus 7, which is 32 over 2. That would give me 16. And then you also have 25 minus 7, okay, 25 minus 7, which would be 18 over 2, which would be 9. So u equals 16 and also 9. So here's the problem. A lot of students get to this step and they go, I've got my answer, I'm done, and they move on to the next problem. You're not finished because the original equation was in terms of x, not in terms of u. Okay, so you've got to go back and you've got to substitute again. So let's copy this. All right, so initially we said that u was equal to x squared. So essentially what I can say here, since u equals 16 or 9, I can say that x squared is equal to 16 or 9 because u is just x squared. So now I can erase this and this. I don't need it anymore. Now I want to set x squared equal to 16, and then I also want to set x squared equal to 9, and I want to get a solution, okay? So if x squared equals 16, using my square root property, I know that x would be equal to plus or minus the square root of 16, which is 4, okay? So over here, if I use my square root property, x squared equals 9, I know x would be equal to plus or minus 3, okay? So we have 4 solutions here. We have that x could be equal to plus or minus 4, so positive 4 or negative 4, and then also plus or minus 3, right? Positive 3 or negative 3. All right, let's look at another one. So we have 2 times the quantity 3x minus 1 squared plus 5 times the quantity 3x minus 1, and this is equal to negative 2. So this one might not jump out at you as being quadratic in form, but realize that you have the same quantity here as you have here, okay? You've got that 3x minus 1, you've got that 3x minus 1. This is typical. See how this is squared and this is basically raised to the first power? If I substitute this quantity with a variable, like again, u, I can solve my equation using the quadratic form, okay? So let's let u be equal to this quantity 3x minus 1. So I'm going to plug in a u there and there. So what would that give me? I would have 2u squared plus 5u is equal to negative 2. And let's scroll down and get some room going. We'll come back up to this in a minute. If I add 2 to both sides of the equation to put this in standard form, I'm going to have 2u squared plus 5u plus 2 is equal to 0. So if I want to use my quadratic formula, I'm going to record the value for a, which is 2, the value for b, which is 5, and the value for c, which is 2, okay? So let's use our quadratic formula to get a solution here. So we have that u is equal to the negative of b plus or minus the square root of, you've got b squared minus 4ac all over 2a. So let's go through and replace some stuff. So negative b is 5, so negative 5, plus or minus the square root of b squared. Again, b is 5, 5 squared is 25. Then minus, you've got 4 times a times c. A is 2 and c is 2. So you have 4 times 2, which is 8, times 2 again, which is 16. If I did 25 minus 16, I'd get 9, and the square root of 9 is 3, okay? Down here, you have 2 times a again is 2, so this is 4. So I've got 2 solutions for u. I've got that u is equal to, you've got negative 5 plus 3, which is going to give you negative 2, and then over 4. So negative 2 over 4 is negative 1/2. Then another solution is negative 5 minus 3, which is negative 8, over 4, which would give us negative 2. So u is equal to negative 1/2 or negative 2. Okay, so we have that again, u equals negative 1/2 or negative 2. And we said that u is equal to 3x minus 1. So we've got to set 3x minus 1, which is again u. So we're putting that there and say this is equal to each solution. So it's equal to negative 1/2 or 3x minus 1 is equal to negative 2. All right, so let's erase all of this. We don't need that anymore. And we'll get our solutions for x. Okay, so on the left-hand side here, this equation, 3x minus 1 equals negative 1/2. I would add 1 to each side of the equation. So I would have that 3x is equal to, you've got 1 minus 1/2. Now you can multiply both sides of the equation by 2 if you don't like working with fractions, or you can just multiply this guy by 2 over 2. It's a little quicker. And you would basically have that 2 minus 1, which is 1, over 2 is your right-hand side. So 3x equals 1/2. We can divide both sides by 3, or you can also multiply by 1/3. Same thing. Makes it easier if you're working with fractions to do that. So you have x is equal to 1/2 times 1/3, which is 1/6. Okay, so that's one answer. All right, so over here, I'm just going to add 1 to each side of the equation. And we know that this is going to cancel. I'll have that 3x is equal to -2 plus 1 is going to be -1. Divide both sides by 3, and I get that x is equal to -1/3. So we get our two solutions here. X is equal to 1/6 or x is equal to -1/3. Of course, you can write it as x equals 1/6, -1/3. Any way you want to notate it is fine. All right, let's look at another one. So suppose we had x to the power of -2 minus x to the power of -1 minus 6 equals 0. So again, look at the fact that this guy right here, it's a -1, but this guy right here is a -2. So it follows that same format, right? If I doubled the -1, I would get to -2, right? So it follows the same format as a quadratic equation. So I'm going to let u be equal to my x raised to the power of -1. Okay. So in this particular case, I'm going to rewrite this using the rules of exponents. I'm going to say this is x to the power of -1 squared. Okay. Again, -1 times 2 is -2. Haven't done anything illegal there. Then minus x to the power of -1, then minus 6 equals 0. So to substitute here, again, this guy is going to be u, and this guy is going to be u. So I'm going to have u squared minus u minus 6 is equal to 0. Okay, so let's erase this. We don't need it anymore. And let's kind of drag this up a little bit. So to put in some visible coefficients here, let's put a 1 here. This is going to be my a. This will be a -1 here for my b. And this will be a -6 for my c. Okay, so for my quadratic formula, I'm going to have that u is equal to, again, you've got -b plus or minus the square root of b squared minus 4ac all over 2a. And again, you keep working with this over and over again, you're going to memorize it. Okay, it's just something you're going to recite in your sleep after a while. So for the negative of b, I know b is -1. The negative of -1 is +1. Plus or minus the square root of, you've got b squared, -1 squared is 1, minus 4 times a times c. A in this case is 1, c is -6. So if you did 1 times anything, it's just itself. So really you get -4 times -6, which is 24. So you can write this as plus 24. We know 1 plus 24 is 25. And we also know that the square root of 25 is 5. Okay, down here we have 2 times a is 1, so this is just 2. So I'm going to get two solutions for u. I'm going to find that u is equal to 1 plus 5, which is 6 over 2, so that's 3. And then also u is equal to 1 minus 5, which is -4, over 2, which is -2. So let's copy this. All right, let's paste this right here. So again, u is equal to 3 and -2. And we said that u is equal to x to the power of -1. So if x to the power of -1 is u, and u is equal to 3 or -2, then x to the power of -1 is equal to 3, or x to the power of -1 is also equal to -2. Now, how do we solve something like this? Remember what an exponent of -1 means. This is basically like saying that we have 1 over x. Now, you can solve it that way, or if you don't want to work with that, you can raise this side to the power of -1 and this side to the power of -1. You can also do that over here. And what's going to happen is power to power rule. -1 times -1 is 1, so you'd have x by itself. And this is equal to, if you have 3 to the power of -1, it's 1/3. So now I'm going to say or. Over here, same thing. X raised to the power of -1, raised to the power of -1. X is just going to be raised to the power of 1, right? -1 times -1 is 1. This is equal to, you've got -2 being raised to the power of -1. So this is basically 1 over negative 2. Okay, so you could write that in a simpler format and just say this is negative 1/2. So x here is 1/3 or x is negative 1/2. Again, I could write this as x equals 1/3, comma, negative 1/2. All right, let's take a look at another one. So we have 3 times the quantity x over x plus 1 squared plus 7 times the quantity x over x plus 1, then minus 6 equals 0. So again, it's the same thing. You have this guy right here and this guy right here that are the same. In one case, it's squared. In the other case, it's raised to the first power. So this is another scenario where you can use your kind of quadratic in form technique to solve. So what I'm going to do is just use a little substitution. So I'm going to let u be equal to this x over x plus 1. So I'm going to sub in there. I'm going to have 3u squared plus 7u minus 6 is equal to 0. So a quick note here, we notice that we have a variable in the denominator here. So we want to make sure that our solution is not negative 1, right? If x ends up being negative 1, if I plugged in a negative 1 there or there, notice how you would get 0 in the denominator, and that is undefined, okay? So you want to guard against that. If you end up with a final answer where x equals negative 1, you've got to throw that solution away because it does not work, okay? So again, let's kind of return to the problem. We've got this set up here. And let's think about this for a second using our quadratic formula. This is my A, this is my B, and this is my C, right? So A is 3, B is 7, C is negative 6. So I've got that U is equal to, we've got negative B. In this case, B is 7, so I'm just going to write it out. Negative 7 plus or minus the square root of, we've got B squared, 7 squared is 49. Then minus 4 times A is 3, so 4 times 3 is 12, times C in this case is negative 6. So that would give me negative 72. So basically you'd have minus a negative 72, which is plus 72. 49 plus 72 is 121. If I took the square root of 121, I would get 11, okay? So this is 11 here, and this is over 2 times A is 3, so 2 times 3 is 6. So U will have, again, two solutions. U will be equal to, you've got negative 7 plus 11, which is 4 over 6. So 4, 6, we know is 2/3, right? You can divide each one of those by 2. You would get 2/3 there. Then alternatively, you've got negative 7 minus 11, which is going to give me negative 18 over 6, which is negative 3, okay? So those are my two solutions for U. So now, if U was set equal to the quantity x over x plus 1, then we know that since U equals 2/3 and also it equals negative 3, I can set x over x plus 1 equal to these amounts. So 2/3, then or x over x plus 1 could be equal to negative 3. So let's solve these two equations. And basically, I'm going to drop this down here. I have x over x plus 1 equals 2/3. What I want to do is multiply both sides of the equation by the LCD. So I've got an x plus 1 and I've got a 3. So I'm going to multiply this side by 3 times the quantity x plus 1. I'm going to do the same thing over here. So 3, let me kind of slide this down. So 3 times the quantity x plus 1. And you'll see that this will cancel and this will cancel. So on the left, you've got 3x is equal to, on the right, you've got 2 times the quantity x plus 1. So that's 2x plus 2. All right, now this is pretty easy to solve. We'll subtract 2x away from each side of the equation. And on the left-hand side now, I just have x, and this is equal to just 2. So x equals 2 is one solution. And again, one of the solutions is that x is equal to 2. I can erase this because I don't need it anymore. Let's put our or here. And let's solve this guy. So I need to multiply both sides by the LCD. In this case, I just have the x plus 1. I don't have a denominator here. I just have negative 3. So I'm going to multiply this side by x plus 1 and this side by x plus 1. And this will cancel with this. On the left, I'll have x, and this is equal to, on the right, you've got negative 3 times, this is a quantity here, so it's negative 3 times x, which is negative 3x, and then negative 3 times 1, which is minus 3. Okay, so let's go ahead and scroll down and get a little bit of room going. We want to add 3x to both sides of the equation. This gives me 4x on the left, and it's equal to negative 3. I can divide both sides by 4, and this will give me x is equal to negative 3/4. So let me erase this, and we'll say that x equals 2 or x equals negative 3/4. So x equals 2 comma negative 3/4. And notice how we did not get a solution for x that violated our domain, okay? Remember, we said initially that x couldn't be negative 1 because if we plugged in a negative 1 for here or here, right, we would get a 0 in the denominator. That is undefined. So you've got to guard against that. So if you ever have a variable in the denominator and you're working with an equation, you've got to look at where would this guy be restricted? Where is it undefined? And make sure you say that, and specifically here, x cannot be negative 1. It's not in this case, so you really don't even need to put that. You just put your solutions here as x equals 2 or x equals negative 3/4. So at this point, I think we pretty much have this down, and we're just going to look at one more problem. So we have x to the power of 2/3 minus x to the power of 1/3 minus 6 equals 0. Again, look how this guy right here is double that of this guy. If I multiplied 1/3 by 2, I would get 2/3. So let's let u be equal to the variable raised to the smaller power. In this case, that's x to the power of 1/3. So I'm going to, again, rewrite this using my rules of exponents. I'm going to say this is x to the 1/3 power squared minus x to the 1/3 power minus 6 equals 0. Everywhere I see x to the 1/3 power, I'm plugging in a u. So I'm going to have u squared minus u minus 6 equals 0. Now, for this particular guy, we can solve this using factoring. It'll be a little bit quicker. We know how to use the quadratic formula, so let's just solve it using factoring. So I'm going to set this up as u and u. Put my 0 over here. Give me two integers whose sum is negative 1 and whose product is negative 6. Well, you can do a negative 3 and a positive 2. A negative 3 and a positive 2. All right, so now we can use our zero product property and set each factor with a variable equal to 0 and solve. So in other words, I would do u minus 3 equals 0 or u plus 2 equals 0. So I'm just going to solve those. This one, I would just add 3 to both sides of the equation. I would get that u is equal to 3. Okay, so one solution is u equals 3. Then over here, I would just subtract 2 away from each side of the equation. I would get that u is equal to negative 2. So, or u equals negative 2. All right, so let's get rid of all this. We don't need it anymore. And let me make that 2 a little bit better. Again, since u is equal to x to the power of 1/3, I can basically say that x to the power of 1/3 is equal to 3, or x to the power of 1/3 is equal to negative 2. Let's erase all this, and let me make that 2 a little bit better. All right, so how can we solve these equations? Well, I can cube both sides to clear the 1/3 power, right? Because if I have 1/3 raised to the third power, it's 1, right? Power to power rule. So if I cube this side and I cube this side, I'm going to get that x is equal to 3 cubed is 27. So x is equal to 27. Then or over here, if I cube this side and I cube this side, I'm going to get that x is equal to negative 2 cubed is negative 8. So or x equals negative 8. All right, so let's erase this. And we can basically state our solution as x equals 27, again, or negative 8. In this lesson, we want to think about applications of quadratic equations. So throughout our study of algebra, we often come across word problems or application problems. So far in our course, we've only discussed word problems that involve solving a linear equation in one variable. Now we're going to go one step further and take a look at some word problems that involve quadratic equations. So I want you to recall that we have a little 6-step procedure that we can use for solving word problems. And although we've introduced this method for use with applications of linear equations, we can also use it in this section as well. So let's just kind of recap this 6-step procedure. I think you'll find it useful if you write it down and kind of go through the steps when you're solving the problem. So solving a word problem, we have that our first step is to read the problem and determine the question or perhaps questions to be answered. You always want to make sure that you understand the question, or again, the questions that you're being asked to kind of answer. It helps you kind of format things in a way, well, what am I trying to find? Then the second step is to assign a variable to represent the unknown. And in some cases, we're going to have to express other unknowns in terms of this variable. Then third, we want to write an equation that describes the scenario we're given. And then fourth, we're just going to solve that equation. Then fifth, we want to write the answer in terms of the question, or again, perhaps questions asked. And then the sixth thing, probably the most important, we want to check the answer using the words of the problem. And we want to make sure that the answer is reasonable. Okay, you're going to see in some of the examples we get today, we're going to have some solutions to our equation that we set up that don't quite work in the context of the problem we're given. Okay, and we'll get to that later on. All right, so the first few problems we're going to look at are going to involve the Pythagorean formula. I know that most of you already know about the Pythagorean formula, but just in case you don't, it doesn't hurt for a little bit of a review. So the Pythagorean formula basically shows the relationship between the lengths of the sides of a right triangle. So again, we know we have a right triangle because of this signature mark here. This is telling us we have a 90-degree angle or a right angle. Okay, so if you have a right angle in a triangle, it's known as a right triangle. Now, with a right triangle, we have this special relationship between the sides, okay? So you have these two shorter sides known as legs. You have this here leg A, which is this kind of vertical measure here. And then you have this leg B, which is this horizontal measure here, okay? And then you have C, which is the hypotenuse, okay? The hypotenuse is always going to be opposite of the right angle, so opposite of this, and it's the longest side. So most of you already know this. The Pythagorean formula tells you that A squared, right, which is basically the measure of leg A, that guy squared, plus B squared, again, the measure of B, leg B squared. If I sum those two amounts together, it's equal to C, which is the hypotenuse, that measure squared. Okay, this is your Pythagorean formula, and it's true for any right triangle that you come across. So using this Pythagorean formula, basically, if we don't know one of the sides of a right triangle, but we know the other two, we can solve for the unknown. Okay, so let's take a look at our first sample problem. All right, so Jason needs to wash a window in a building that is 12 feet from the ground. To avoid a fence, he decides to rest the ladder against the building. For stability, Jason decides he should place the ladder 9 feet away from the building. How long of a ladder will Jason need? Okay, so the first thing we need to understand, again, is what am I being asked to find? And in this case, it's this little question here, right? So how long of a ladder will Jason need? So we'll just highlight that. That's what we're trying to find. So when we go to assigning a variable, we're just going to let x represent exactly what we're trying to find, which is the measure of Jason's ladder. And this is going to be in feet because we're working with feet in the problem. So let's go down here to a fresh sheet. We're going to say that we're going to let x be equal to the measure of Jason's ladder and of course this is going to be in feet. Okay, so in feet. All right, so I'm not going to write feet every time. I'm just going to work with the number parts. We're just going to understand that we're working with feet. All right, so to help us understand what's going on, we have this little illustration here. It's not perfect, but it'll just give you an idea of what's kind of happening in our problem. So when we started out, we said that Jason wanted to wash a window in a building that is 12 feet from the ground. So this guy right here, this represents our window. Okay, that's in our drawing. And basically you could say that it's 12 feet from the ground. So from right here to right here, that measurement, let me kind of draw a little vertical line. Okay, not perfect, but it'll have to do. So this guy's going to be 12 feet. Again, I'm just going to put 12. And then also, it tells us that for stability, Jason decides he should place the ladder 9 feet away from the building. So the ladder, we can't see it because it's hidden in the grass, but let's just say it's about right there. So from right there to right here, let me use a different color. So from right there to right here, that horizontal measure is going to be 9 feet. So let me again just draw a little horizontal line. Okay, again, not perfect, but you get the idea. So this guy is 9 feet. I'm just going to put 9. And I can put my little symbol here. This is going to be a right angle. So I've got that symbol there. So we have a right triangle, right? We have that this guy here, this horizontal leg is 9. This guy right here, this vertical leg is 12. And I'm solving for this guy right here, which is the length of his ladder. This is exactly what I need to find. I can just put this as x right here. This guy is going to be the hypotenuse, okay? So essentially I can say that, again, for my Pythagorean formula, a squared plus b squared equals c squared, where a and b are the lengths of the two shorter sides or the legs, right? So we know that's 9 and 12. So we just plug in and say that we have 9 squared plus 12 squared, okay, and it doesn't matter the order that you do that in, is equal to, instead of c, I just have x, so I'm going to say this is x squared, okay? So 9 squared we know is 81, plus we know 12 squared is 144. This equals x squared. And 81 plus 144 is, of course, 225. So we get that x squared, okay, x squared is equal to 225. So we can solve this with our square root property. We know that x would be 15 or negative 15, right? Take the square root of each side. So square root of this side is equal to plus or minus the square root of this side. And let me kind of scroll down to get a little bit of room going. And we can basically say again that x is equal to plus or minus 15. Now, does it make sense? Okay, does it make sense for the measure of this ladder to be negative 15? No, it's nonsense. Okay, so that's where, checking your answer when you think about kind of the steps we gave makes a lot of sense. So if you incorrectly said that the ladder could be 15 feet or negative 15 feet, when you go to check that, you can say, okay, that doesn't make sense, right? A ladder can't measure negative 15 feet. That's complete nonsense. So you just have to throw that solution out and say that x, or the kind of length of the measurement of that ladder, is going to be 15 feet, okay? So I'm just going to write that in there and say this is 15, or again, 15 feet. So let's go back up. And again, we can just kind of write a little sentence to describe our answer. So how long of a ladder will Jason need? Well, we'll say that Jason needs a ladder. Jason needs a ladder that is 15 feet long. Okay? So checking this is really, really easy. Again, we just go through our Pythagorean formula. And it's easier to check something like this by looking at the picture again, just so you get an idea what's going on. Again, we said that with Jason, he needs to wash a window in a building that's 12 feet from the ground. So this is where the window is, and this is where the ground is. So the distance from here to here, that's 12 feet. Okay, so that's where we got the 12 from. And then to avoid offense, he decides to rest the ladder against the building. So that's why this ladder is drawn in this manner, okay? And then basically it says that for stability, Jason decides he should place the ladder 9 feet away from the building. So from here to here is 9 feet. That's where we got that 9 from. Okay, so this part all checks out. So then we're asked, how long of a ladder will he need? Well, again, we see that we have a right triangle, and so we can use our Pythagorean formula. We plugged in, we got 9 squared plus 12 squared equals x squared. X was the length of the ladder. And so we got 81 plus 144 on the left side of this, which is 225. So we ended up with x squared equals 225. We took the square root of each side, right? And we found that we had x equals plus or minus 15. We threw out negative 15 because it didn't make any sense. So that's how we got our solution, where we said that Jason needs a ladder that is 15 feet long. Okay, so this solution is correct. All right, let's go ahead and take a look at another one. So we have that Larry and Steven were both parked in the same parking garage. Larry leaves first and drives north at 50 miles per hour. 1 hour later, Steven leaves and drives east at 70 miles per hour. How long after Larry starts driving does it take for the two cars to be 290 miles apart? So again, we want to understand the main question, and here it's just to find how long after Larry starts driving does it take for the two cars to be 290 miles apart. So for this problem, we're going to end up using our Pythagorean formula, and we're also going to use the distance formula that we see with motion word problems, right? The distance equals the rate of speed times the amount of time traveled. All right, so before we kind of get into that, though, we need to assign a variable to represent the unknown. In this case, we're going to end up having kind of two unknowns because we don't know how long Larry's going to drive for, and we also don't know how long Steven's going to drive for, okay? So what we're going to do is, since Larry leaves first, we're going to say that x is the amount of time that Larry drives for before the two are 290 miles apart, okay? So let's go down here to a fresh sheet, and I'm just going to say we're going to let x be equal to the amount of time, and I'm just going to put for Larry, okay? And we know what that means. It's going to be specifically in hours, and it's going to be the amount of time that Larry drives for before, again, the two cars are 290 miles apart. Now, for Steven, we can kind of base his time on Larry's, right? We know Larry's time is x. Well, for Steven, we know that 1 hour later, Steven leaves. So he's been driving for an hour less, at this point when they are 290 miles apart. So I can just go x minus 1 to represent Stephen's time. Okay, so we're going to say then, I'll do that in a different color. So we'll say then x minus 1, this quantity is the amount, again, of time for Stephen. Okay, we'll just make it nice and simple like that. You could write out something that's really long and say it's the amount of time for Stephen, in hours before they're 290 miles apart, but you kind of get the idea, and we want to make it as short as possible. All right, so the next thing we want to do is just come down to a little table, just organize our information so that we know what's going on. So our distance formula, in case you forgot, the distance traveled, which I'm going to say is d, is equal to the rate of speed, which is r, multiplied by the amount of time traveled, which is t. Okay, so the rate of speed is in miles per hour, the time is in hours, and the distance is going to be in miles. Okay, and then we have two participants here. We have Larry, and then we have Stephen. Okay, so those two guys are involved in the problem. So what information do we have? Well, we know the time because we said that Larry's going to be driving for X hours when the two are 290 miles apart. And we said that Stephen, since he drives an hour less, is going to be driving for X minus 1 hours, again, when they're 290 miles apart. Now, the rate we can get directly from the problem. It tells us specifically that Larry leaves first and drives north at 50 miles per hour. So this 50 miles per hour is going to be his rate of speed. And then for Stephen, he leaves and drives east at 70 miles per hour. So 70 is going to be his rate of speed again in terms of miles per hour. So let's just fill this in. For Larry, it's going to be 50 miles per hour. For Stephen, it's going to be 70. Now, if I have a rate of speed and I have a time, I have a distance, right? Because I could just multiply. R times t gives me d. So 50 times x is 50x. And that's my distance that Larry's going to travel, again, when they're 290 miles apart. So for Stephen, he's going to have traveled 70 times the quantity. Remember, this is a quantity and this is multiplication. So put parentheses. So times the quantity x minus 1. And you can go ahead and simplify this now because you're going to have to later. You can just say this is 70x minus 70. So we'll write this as 70x minus 70, just so that we have it ready to go. Okay, so before we kind of set up our equation, I want you to think about something, because usually at this point, people make a drastic mistake. They're used to kind of solving these in another scenario, kind of with the opposite direction travel. With that one, they end up saying, okay, well, the distance Larry travels, which is 50x, plus the distance Stephen travels, which is 70x minus 70. They sum those two amounts and they say, okay, well, that's got to be equal to 290, okay? This is wrong. This is what we saw kind of earlier in the course. This is not the current setup, okay? What we have here, and just to kind of illustrate what's going on, I drew a little picture, a little illustration. And basically what we have, again, is another application of the Pythagorean formula, because we end up with something that is a right triangle, okay? So we have that Larry is driving north. So you can picture him starting from here. Let's just say that's the parking garage. And he drives north, which on every map that you look at, that's basically going up, okay? So this is going to be a vertical leg for the right triangle. And we know that measure, the distance, if I go back, is going to be what? It's 50x. So let's go back here. And I'm just going to write this in as 50x. And we know that's for Larry. So I'm just going to put a little arrow here and say that's L for Larry. Okay, that's his distance. That's, again, from here to here. That's the point he's going to be at when these two guys are 290 miles apart from each other. Now, for Stephen, let me put a little S here and go this way. He's got this horizontal leg. So this guy to this guy, that distance there, again, if we go back up, that's 70x minus 70. So let me put this here as 70x minus 70. Okay, so you can obviously see what's going on here. We've got our two legs for this right triangle. And again, the formula is that a squared plus b squared. Okay, we square each of the legs and we sum those amounts together. And this is equal to the hypotenuse squared. So c squared, again, normally this is c. But in this case, we have kind of expressions involved. So we just kind of plug those in and work with those. So we end up with, let's just say 50x, that quantity squared, then plus this guy is the quantity 70x minus 70. The whole thing is squared, so make sure you wrap it in parentheses. And this equals our c, or our hypotenuse, is going to be 290. So that amount, that's going to be squared, okay? So we're going to just copy this and go to a fresh sheet because we'd run out of room here because this is going to be quite tedious. So let's just paste this in here and let's get started. All right, so for 50x squared, if we wanted to simplify that, I would need to square 50 and also x. So that would give me 50 squared times x squared. Now, 50 squared is 2,500, so let me just replace that and say it's 2,500. Okay, so then plus. Now, don't make the mistake of doing this. A lot of students, again, I've said this throughout the course, they do what? They say this is 70x squared minus 70 squared. Okay, that is wrong. This is wrong. Don't do that. Remember, if you have something in here with addition or subtraction, you've got to expand it. Okay, remember our special products formula. You can use that here to do this pretty quickly. You're going to square the first guy, which is 70x, that whole thing squared, right? So the whole thing is squared. So it's 70 squared, which is 4,900, times x squared. Okay, then you're going to have minus. You're going to have 2 times this guy times this guy. So it's 2 times 70x times 70. Okay, and we'll just go ahead and crank that out real quick. 2 times 70 is 140. Then times 70 again would be 9,800. So basically what you'd have is minus 9,800x here. So minus 9,800x, or you could say 9,800x, whatever you want to say. And then lastly, you need to take this 70, the last term there, and square it. So we're going to go plus 70 squared, we already know is 4,900. So this is 4,900. Okay, so that's this side right here, and this equals 290 squared is 84,100. Let me slide this down so I can fit this all in one line. So 84,100. Okay, so we have kind of some big numbers involved here. So let's do some simplifying, and then I'll show you what we can do to kind of make this as easy as possible. All right, so 2,500x squared plus 4,900x squared, those are like terms, so we can combine them. So if I had 2,500 and 4,900, I get 7,400. So this is 7,400x squared. Then minus 9,800x, I can't do anything with that as of yet. So we'll just leave that as it is. And then what I can do over here, I'm going to subtract 84,100 away from each side of the equation. Okay, and what that's going to do is that's going to give me 0 over here on the right side. Okay, because I'm solving a quadratic and I want it in the format of ax squared plus bx plus c equals 0, so I can use my quadratic form. Okay, so 4,900 minus 84,100 is going to give me minus or negative 79,200. Again, this equals 0. Now, if you want to plug these into the quadratic formula as they are, you can. Most of you, I know pretty much all of you are going to be using a calculator. I'm using a calculator. If you're working with bigger numbers or smaller numbers with a calculator, it doesn't really matter, right? It does the calculation for you. But just to make this a little easier, a little simpler. So what we'll notice here is that each of these numbers ends with 2 zeros. This guy over here is a 0, so it's not going to matter. But if they all ended 2 zeros, they're divisible by 100, right? So if I divided every part of this equation by 100, on the right, 0 divided by 100 is still 0, so that's fine. Basically, I would just knock 2 zeros off from everything, right? So that makes it a lot simpler, right? You have 74x squared minus 98x minus, and this comma would disappear. You'd have 792, and this equals 0, okay? Perfectly mathematically legal to do that. And you would notice that you could also still divide each part by 2. So if you wanted to make it even simpler, you could say that 74 divided by 2 is 37, so 37x squared. And then 98 divided by 2 is 49, so minus 49x. And then minus, if you take 792 and you divide by 2, you would get 396. And we can say this is equal to 0. Okay, so this is a lot simpler, a lot easier to work with. So let's kind of drag this up here and see what we got now. So we're going to use our quadratic formula. So again, this is going to be A, this is going to be B. Okay, it's the whole negative 49. And this is going to be C, again, the negative 396, okay? And I circled the negative ones because sometimes you get confused and you try to just take the number part without the sign. When it's positive, obviously, it doesn't matter, right? You're not bringing a sign with you. It's just positive, so it doesn't have a sign in front of it. All right, so with the quadratic formula, again, in case you have forgotten it, x is going to be equal to the negative of b plus or minus the square root of, you've got b squared minus 4 times a times c. This whole thing is over 2a. So all I'm going to do is just plug in. Okay, very, very easy. So for negative b, again, b is negative 49. The negative of negative 49 is 49. Plus or minus, you've got b squared, so you'd have negative 49 squared. So let's just go ahead and do that real quick. If I square negative 49, I get 2,401. So let me write that in. 2,401 That's kind of hard to fit in there. So let me redo this. So square root of 2,401, again, minus 4 times. For A, I have 37. And then for C, I have my negative 396. And we can crank this out now or come back in a minute. Let's just come back in a minute. For A, we have what? We have 37, so let's plug that in there. All right, let's do our calculation. So negative 4 times 37 is negative 148. Then times negative 396 is going to give me 58,608. So let's just put plus 58,000, again, 608. If we sum 2,401 and 58,608, we get 61,009. Okay, so let's write that there. So 61,009. Then down here, 2 times 37, we know from earlier is 74. Okay? All right, so what is the square root of 61,009? Well, if you punch that up on a calculator, you're going to get 247. So let's erase this and put 247. Now, we have two cases here, but you're going to see that one of the cases ends up being nonsense, right? Remember, we're solving for x, which is the amount of time that, in this particular case, Larry's going to travel for or drive for before the two cars are 290 miles apart. So you know that you can't have a negative amount of time. That wouldn't make sense in this scenario. I can't say, well, he drove for negative 18 hours, as an example. Okay, what does that mean? It doesn't mean it's nonsense, so you have to throw it out. So the one of these guys that's going to make it negative, we would just immediately exclude that, okay? So the first scenario would be that x is equal to 49 plus 247 over 74. So we keep that one. The other scenario is what? It's x is equal to 49 minus 247 over 74. This is going to end up being negative, so you can just throw this out, okay? You don't need to worry about that solution at all. So focusing on this one, 49 plus 247 is 296. So if you had 296 over 74, you would have 4. Okay, so nice and simple. So x equals 4. Again, that tells me that Larry drove for 4 hours before the two cars were 290 miles apart. Again, x was the amount of time for Larry. X minus 1 was the amount of time for Steven. So this guy is 4 and this guy is 3, right? Because 4 minus 1 is 3. So again, to officially answer this, how long after Larry starts driving does it take for the two cars to be 290 miles apart? We'll say Larry drives for 4 hours before the two cars are 290 miles apart, okay? And if you want to check this, again, it's easy to go to the diagram and kind of visually see what's going on. You want to mark down some information that Larry's going at 50 miles per hour and Steven's going at 70 miles per hour. So let's go to the little drawing we have and let's see if we can make sense of this. We can erase all this. We can actually leave the a squared plus b squared equals c squared. We'll actually use that. So if I plug in a 4 for x, I'd have 200. So that's for Larry. We know that he drives 200 miles from here to here, and that's basically over the span of 4 hours, and that's how far he's going to have traveled when he gets to this point here when they're 290 miles apart. And then for Steven, you can plug in a 4, which is what x is. You get 70 times 4 is 280. 280 minus 70 is 210. Or you could, again, do it kind of manually and say, okay, well, he was going 70 miles per hour. He only drove for 3 hours. 70 times 3 is 210. So either way, you get 210 as his distance from here to here, okay? So again, we know about the right triangle. If this is 200 and this is 210, plugging in, if one is 200 and the other is 210, if we sum those two squares, it should be this guy right here squared. So is that true? 200 squared is what? Well, punch that up on a calculator, you're going to get 40,000, okay? 210 squared, punch that up on a calculator, you're going to get 44,100. And if you sum those two amounts together, you are going to get 290 squared, because that's going to be 84,100, okay? You can easily see that. 40,000 plus 44,100 is 84,100. So we can say here our answer is correct. Larry drove for 4 hours before the two cars were 290 miles apart. All right, so another common type of problem in this section involves finding an unknown area. So generally speaking, these problems are going to deal with some type of rectangular shape. This could be a pool, it could be a garden, it could be a quilt. The example we're going to see next is going to be a rug, okay? So something rectangular in nature. So what I want to cover really quickly is just the formula for the area of a rectangle. So we have a rectangle on our screen, we have our length, and we have our width. Okay, so the area of a rectangle, we'll put A here, is equal to the length, which I'm going to put capital L, times the width, which is capital W. Okay, so that's the formula for the area of a rectangle. You might want to write that down because we're going to use it immediately in the next problem. So just as a quick example, suppose I said that the length here was 8 inches, and suppose I said the width here was 6 inches, okay? And I said, well, what's the area of this rectangle given this information? Well, the area, I'll just put capital A, is equal to what? It's 8 times 6, which is 48. You're just multiplying. And then inches times inches, you multiply your units. That's going to be inches squared, or you could say square inches. So we're going to say this is 48 square inches, okay? And let me make this Q a little bit better. Okay, so again, 48 square inches when we have a length of 8 inches and a width of 6 inches. All right, so again, let's put this formula to immediate use. So we have here for our sample problem that Jamie wants to put a rug in a bedroom that is 15 feet long and 12 feet wide. She wants to leave a strip of uncovered floor that has a uniform width around the rug. After looking at pricing information, she decides that she can afford to buy a rug with an area of 108 square feet. Okay, so what are the dimensions of the rug? So again, what are we being asked to find? Well, given the fact that she can afford to buy a rug that has a maximum area of 108 square feet, we want to know what are the dimensions of the rug, okay? Well, to solve this problem, if you haven't seen it before, it might be a little challenging for you to kind of set it up, okay? So usually what you do with this is you draw a little diagram, and I have that already set up. And what you'll see here is that the entire rectangle is meant to represent the bedroom, okay? And then you have this kind of smaller rectangle, which represents your rug. And then the brown you see, that's the strip of uncovered floor, okay? That's around the rug, okay? And that's actually the key to understanding this problem. So when we go back up, I just want to read this part one more time. She wants to leave a strip of uncovered floor that has a uniform width around the rug. This is very important. So this uniform width around the rug, okay? Let me go back down, and we're just going to label a few things. So what do we know? We know the length of the bedroom, or the measurement from here to here, is 15 feet, okay? That's given in the problem. We know the width, the measurement from here to here, is 12 feet. That's given to us in the problem. We also know that this kind of strip of uncovered floor has a uniform width. So in other words, I know from here to here, and then from here to here, and from here to here, and from here to here, this is all going to be the same all the way around. The width is all the same, okay? So the key to this problem is letting a variable like x, or whatever you want to use, represent that uniform width for that strip of uncovered floor, okay? So I'm just going to say this is x, this is x, this is x, and this is x. Okay, so given the information that we have now, can you see how you would set up and find the dimensions of the rug? Okay, so for the rug, we want to know what's the length and what's the width. Well, for the length, I know the length of the bedroom. It's given to me, it's 15 feet, so that's from here to here. If I want the length of the rug, well, I need to subtract out kind of from here to here and from here to here, okay? So what's that measure? And I kind of went over there, so let me draw that a little bit better. So what's that measure? Well, it's going to be 15, the total amount, minus this, which is x, okay? This is x, and then minus this, which is x. So 15 minus x, which is going to be 15 minus 2x, okay? So that's going to be my length of the rug. Now, for the width, it's a similar thought process, okay? The width is going to be from here to here. And again, I just want to think about the width of the whole room, which is 12 feet. So I'm just going to put 12 there. And I want to subtract out this guy right here, which is x. And I want to subtract out this guy right here, which is also x. So 12 minus x is 12 minus 2x, okay? So now I have a length as an expression, 15 minus 2x, and I have a width as an expression, 12 minus 2x. So let's copy that real quick, and I'm just going to paste that there. And what we know from our problem, it tells us that she can afford to buy a rug with an area of 108 square feet, so we're going to assume that that's what she buys. So my length times my width gives me my area. So what I'm going to do is I'm going to say 15 minus 2x, that quantity, that's my length, multiplied by the quantity 12 minus 2x, that's my width. This should equal my area, and we're told that the area is 108 square feet, so I'm just going to put 108, okay? So I'm going to solve this equation for x, and that's going to allow me to find out what is the length and what is the width for my rug that Jamie has, okay? So 15 minus 2x times 12 minus 2x, we're going to use FOIL for that. So 15 times 12 is 180, and then 15 times negative 2x is minus 30x. Negative 2x times 12 is minus 24x. If I combine like terms, I'm going to have negative 54x, so minus 54x. All right, so then we have negative 2x times negative 2x, which is going to be plus 4x squared. And then this is just equal to 108. Okay, so let me kind of rearrange things here. Let me put this as 4x squared minus 54x plus 180 is equal to 108. Now, what I want to do is subtract 108 away from each side of the equation so that I can have 0 on the right side, and I can go ahead and use my quadratic formula, or you could factor, whatever you want to do, okay? So in this case, I'm going to have 4x squared minus 54x, and then plus 180 minus 108 is going to be 72. This equals 0. Now, if you want to do this, this is an optional step. You don't need to. You can divide each part here by 2. Okay, that's going to give you smaller numbers to work with. So if I divide this by 2, this by 2, this by 2, and this by 2, I'm going to get 2x squared minus 27x plus 36 equals 0. Okay, that's just something I did to give us smaller numbers to work with. Again, completely optional. All right, so now let's use our quadratic formula. Again, you can solve this one with factoring, but I'm going to use the quadratic formula. So this guy right here, this is going to be A. This guy right here, this is going to be B. This guy right here is going to be C, okay? So I'm going to plug into x equals the negative of b plus or minus the square root of, you've got b squared minus 4ac, the whole thing's over 2a, okay? So the negative of b is negative 27, so just plug that in there. Then b squared, you've got negative 27 squared. 4 times a times c, a is 2, c is 36, and then a again is 2. Okay, so we filled all this in. Now we can just kind of crank it out. The negative of negative 27 is 27. Okay, so that's easy enough. Negative 27 squared is 729. So this would be 729. Negative 4 times 2 is negative 8. And then negative 8 times 36 is negative 288. So this is basically minus 288. If I do that calculation real quick, I'm going to get 441, right? 729 minus 288 is 441. If I took the square root of 441, I would get 21. Okay, so this is 21 here. And then 2 times 2 is 4. Okay, so we're going to get 2 answers. You're going to find that one of them doesn't work, but we'll get to that in a minute. So 27 plus 21 is going to be 48. 48 divided by 4 is 12. So x equals 12. And then also 27 minus 21 is 6. 6 over 4, you can say that's 3/2 or 1.5. So let's take these back to our illustration. And we're going to see if they make sense. Okay, so let me paste this up here. So can x be 12? Remember, I'm plugging in for x in each case. So I'm plugging in here and here. Well, 2 times 12 is 24. 15 minus 24 is negative. Okay, it's going to be negative 9. Does it make sense for this rug to have a length of negative 9? Okay, no, it can't be negative 9 feet. That doesn't make any sense. It's nonsense. So you get that when you solve these problems. You just have to reject one of the solutions. So go ahead and throw that out. Okay, you can't use that. Can we use 3/2? Yes, we can. 3/2 is 1.5. If you multiply 2 by 1.5, you get 3, okay? So what you'd have in each case, you could just replace this with 3 and this with 3. 15 minus 3 is 12, so that's the length of the rug. And 12 minus 3 is 9, so that's the width of the rug, okay? So we basically found our answer for our problem. So what are the dimensions of the rug? We'll say that Jamie's rug, okay, Jamie's rug has a length of 12 feet and a width of 9 feet. Okay, is that consistent with what we're told in the problem? Well, 12 times 9 is 108. Feet times feet is feet squared or square feet. So that does match up with this, okay? But you can also check to make sure that it is consistent with the rest of the problem. So when we come back to our little illustration, again, we just want to check that this 1.5, this figure matches up with what we got, right? So this 1.5 is the width of this strip of uncovered floor, which has a uniform width. It's supposed to be the same all the way around. So it's 1.5 all the way around. Let me write that like this. Okay. So does that make sense? Well, if the length or the measurement from here to here is 12, and I add 1.5 for this and 1.5 for this, well, yeah, 12 plus 1.5 plus 1.5 is 12 plus 3, that's 15. That's this guy right here, the length of the bedroom. Okay, so that makes sense. Same thing's going to happen for the width. So the measurement from here to here, we know that's 9, then plus another 1.5, plus another 1.5. 9 plus 3 is 12. Again, that's given to us in the problem. So that checks out. And we already checked the fact that the rug matches up and it gives us 108 square feet. So we can basically say we're good to go. This rug has a measurement of 12 feet for the length and 9 feet for the width. All right, so let's wrap up the lesson and talk about another common problem you see in this section. We're going to be dealing with the height of a propelled object in feet. So when we get to this section, we basically have a little formula that we work with. If air resistance is disregarded, the height of an object that's propelled directly upward can be thought about with this formula. So we have h is equal to negative 16t squared plus v sub 0 times t plus s sub 0. So when you're in this section in your algebra course, you're going to be given this formula. They're going to give you stuff to plug in, and then you're going to have to solve for something, okay? So h is the height of the projectile in feet, t is the number of seconds, v sub 0 is the initial velocity in feet per second, and s sub 0 is the initial height in feet. So when we're talking about height, if I get a height of 0, that means I'm on the ground, okay? If I get a height that's positive, let's say it's 50, let's say for h, again, it's 50, that means I'm at a height of 50 feet in the air, okay? If I get an initial height in feet, it's the same thing. If I got 50, that means I'm launching from 50 feet. All right, let's look at a sample problem. I think you'll find this to be very, very straightforward. A toy rocket is launched vertically upward from an initial height of 500 feet. The initial velocity is 20 feet per second. Find out how long before the rocket will hit the ground. Okay, so obviously we're just answering this part right here where it says to find out how long before the rocket will hit the ground. We're just going to take the formula. Let's go back for a second. And we're going to grab this guy, and I'm just going to rewrite it right here real quick. So h is equal to, you've got negative 16t squared. And you got to be careful here because the t gets confused with a plus sign. So I'm going to put that in a different color. So plus, you've got your v sub 0 times t, or you could say t times v sub 0. So let's put v sub 0 times t. And again, you've got another plus sign, so let's do that in a different color. And then you have your s sub 0. Okay, so this is your formula that you're working with. Now, we can plug in a lot of information here. It says that the initial height is 500 feet. S sub 0 is your initial height. So you can just go ahead and erase this and put 500 there. And then it says the initial velocity is 20 feet per second. So that's this v sub 0 here. So I'll erase that and put a 20 there, okay? So now we have two variables involved. I have h and I have t. But it says find out how long before the rocket will hit the ground. We already said that when the rocket hits the ground, h is 0, right? That's the height. So I can just replace h with 0. And all I have here is a standard quadratic equation, right? So I have negative 16t squared plus 20t plus 500. If I replace t with x, it's going to look very familiar for you, okay? And I'm not going to keep it this way. I'm going to keep it with t because that's consistent with our formula. But if you were struggling and you couldn't kind of grasp what's going on, just replace it with x, solve it, and then go back and replace that for t, okay? Not a big deal. So I can solve this using the quadratic formula. I can also solve this particular one by factoring. What I'm going to do to make this a little bit simpler, I'm going to divide everything by 4, just so we have smaller numbers to work with. So divide this by 4, this by 4, this by 4, and this by 4. I'm going to get, and I'm also going to kind of rearrange things. So I'm going to get negative 4t squared, then plus, I'm going to have 20 over 4 is 5, so 5t, and then plus 500 divided by 4 is 125. This equals 0. Okay, let's go ahead and plug into the quadratic formula. So we know that what? We know that this guy right here, this negative 4 would be A. We know this guy right here, this 5 would be B, and this guy would be C, okay, this 125. So instead of x, we have t, so we're going to say t is equal to you've got the negative of b. b is 5, so negative 5, plus or minus the square root of, you've got b squared. Again, b is 5, 5 squared is 25, minus 4 times a is negative 4, times c is 125. And I'll do this in a minute. This is over 2a is negative 4, so 2 times negative 4 is negative 8. Okay, so negative 4 times negative 4 is plus 16. So let's just put plus, you'd have 16 times 125. That's going to be 2,000, okay? So 25 plus 2,000, you do this all in one shot. This is 2,025. If you punch up square root of 2,025 on a calculator, you're going to get 45, okay? So this guy's 45. Now, one of these solutions you're going to throw out, okay? Because we're solving for t, which is time. So it's got to be a positive value or 0, okay? It's basically got to be non-negative. If you end up with something like negative 800 seconds, what does that mean, right? It doesn't mean anything. Again, it's nonsense. We've seen that throughout this kind of lesson. If you get something that doesn't make sense, just reject it, throw it out, okay? So the first one would be negative 5 plus 45. So let me kind of do that over here. So t equals, so negative 5 plus 45, which would be positive 40, over negative 8. This would end up giving me negative 5 seconds, which again doesn't make sense. So we're just going to throw that solution out, okay? We don't need it. Then t is equal to, the other one is negative 5 minus 45, which would be negative 50. And then divided by negative 8, negative over negative is positive. I can also simplify by dividing each by 2. So this would end up being 25 fourths. Now, in decimal form, that's 6.25, and that's what we're going to use. So let me erase all this. We don't need any of it anymore. So find out how long before the rocket will hit the ground. Well, we found that it's going to happen at 6.25 seconds, right? So we'll say that the rocket will hit the ground at 6.25 seconds, okay? And again, a very, very easy problem. Very, very easy if you get this question on homework or tests. You just plug into the formula and you're basically just have to set up your quadratic equation and solve. Okay, so how about checking something like this? What would we do? Well, again, we just go through the formula again. It's h is equal to, we have your negative 16 times t squared. For t, I've got 6.25. Again, I can plug in a fractional form here to make it a little simpler. So I'm going to put 25 fourths, this guy squared. Then plus v sub 0, the initial velocity was 20. So we're going to put 20 times, you've got your t, which again, I'm going to put 25 fourths for that. And then you've got plus your s sub 0, which is 500. That was the initial height in feet. So that's 500 feet. Okay, so h is supposed to be 0. So we just check this, make sure we got the right answer. So let's go back down. So 25 squared is 625, 4 squared is 16. So this would be 625. I'm going to write that a little better. So 625 over 16. This guy's going to cancel with this guy and give me a negative 1. So this would basically be negative 625 here. And most of you can already see this is going to work out. This cancels with this and gives me a 5. 5 times 25 is 125. So basically what you have is 125 plus 500, which is 625. And then that's being added to negative 625, so that does give you 0, right? You end up with 0 equals 0. So this is consistent with what we're told in the problem. So we can say here that our answer or solution is correct. The rocket will hit the ground at 6.25 seconds. In this lesson, we want to review solving quadratic inequalities. So a quadratic inequality is of the form, we have ax squared plus bx plus c is less than 0, where we can say that a, the coefficient of x squared, b, the coefficient of x to the first power, and c, the constant term, represent any real number with one exception. We can't have a allowed to be equal to 0. Because if a is 0, our x squared term would disappear, and we'd no longer have a quadratic inequality. Now, additionally in this definition, we can say that our less than here could be a less than or equal to, a greater than or equal to. All right, so how can we solve a quadratic inequality? Well, there's quite a few different methods that you can use. We'll talk about a method that relies on graphing kind of later on in the course. Graphing is good to conceptualize what's going on, but it's not necessarily the quickest method. In most cases, it's not going to be quickest. So we're going to focus on a method that relies on test values. So for solving quadratic inequalities, the first thing we want to do is we want to write the inequality as an equation and solve. So what this is going to do is it's going to give us our boundaries, okay? Or some people will call them endpoints. Some people will call them critical values. Now we're going to use the solutions from the equation to set up intervals on the number line. And again, we'll see that in a moment when we look at an example. Then this is the important part here. We're going to substitute a test value from each interval to determine the solution set. Now, the problems we're going to look at today are going to be inequalities such that when we transform them into equations, these quadratic equations are going to have real number solutions, and more specifically, they're going to have rational number solutions. So these are going to be kind of easier examples just to get the concepts down. You can work with these when the equations have complex solutions and also when they have irrational solutions. But we'll talk about that later on, again, when we revisit this topic using graphing. All right, so let's go ahead and take a look at the first example. So we have x squared minus 6x is greater than 16. So the first thing I'm going to do is kind of write this where my quadratic expression is on the left side and 0 is on the other side, okay? So I can do that by just subtracting 16 away from each side of the inequality. And I'll just write this over here. This would cancel and become 0. I would have that x squared minus 6x minus 16 is greater than 0. Okay, so now what I want to do is I want to change this inequality into an equality. So all I got to do is change this greater than symbol to an equal symbol. So I'm going to make this into x squared minus 6x minus 16 is equal to 0. So I can solve this using factoring. I can solve this with my quadratic formula. Whatever you want to do, it's pretty easy to solve this with factoring. So let's just do that. So this would be an x, and this would be an x. So give me two integers whose sum is negative 6 and whose product is negative 16. We know that would be negative 8 and positive 2. So now I can just set each factor equal to 0 and solve. So I would have x minus 8 is equal to 0, or I would have that x plus 2 is equal to 0. For this one, I can add 8 to each side of the equation, and I'll get that x is equal to 8. For this one, I can subtract 2 away from each side of the equation. I'll get that x is equal to negative 2. So let's erase all of this. We don't need any of it anymore. We just need these solutions. So at x equals 8 or at x equals negative 2, we're basically saying the left side of this quadratic inequality is going to be 0. So here's 8 and here's negative 2. So what I'm going to do is I'm going to put a vertical line at each to kind of separate the number line into intervals. So anything less than negative 2 or anything to the left of negative 2, let's just call this interval A for reference sake. Anything between negative 2 and positive 8, let's call this interval B for reference sake. And anything that's greater than 8, or you can say anything to the right of 8, let's call that interval C, again, for reference sake. So 3 intervals on the number line. What we're going to do is test a value in each interval and see if it works in our inequality. And the reason this works is that, again, at 8 or negative 2, the left side here is going to be 0. Now, all other numbers other than 8 or negative 2 will make the left side either negative or positive. And the sign of the quadratic expression can only change from positive to negative or negative to positive at a number that makes it 0. So this means that if a number in the interval that we test, so if a number in interval A or a number in interval B or a number on interval C, if a number in one of those intervals satisfies the inequality, then every number in that interval will satisfy the inequality. The reverse is true. If a number in that interval does not satisfy the inequality, then no number in that interval will satisfy the inequality. So in interval A, let's just go ahead and choose something like negative 4. That would be a good test point. And we can try that in this guy right here. So let's plug in a negative 4 everywhere we see an x. And so we would have negative 4 squared, which is positive 16. Then negative 6 times negative 4 is plus 24. Then you'd have minus 16, and this is greater than 0. Well, we know that 16 minus 16 is 0, so you have that 24 is greater than 0, which is true. So I'm just going to put for interval A that this is true. Okay, so every number in interval A would work. Now, let's choose something in interval B. Using 0 is always pretty quick. So let's choose that. Let's plug in a 0 for each x. You would have that negative 16 is greater than 0, which is false. So for interval b, we'll say this is false. And then for interval c, let's choose a value of 10, because that would be pretty easy to work with. So 10 squared is 100, minus 6 times 10, which is going to be 60. Then minus 16 is greater than 0. 100 minus 60 is 40. 40 minus 16 is 24. 24 is greater than 0. This is true. So for interval c, we'll say it's true. Okay? So let's erase all of this. We don't need this anymore. And you can label this visibly. You can say that interval a is true, interval b is false, and interval c is true. In most of the situations you're going to look at, when your quadratic inequality sets up as a quadratic equation with real number solutions, you're going to basically have 3 intervals where either the left interval and the right interval are going to work and the middle doesn't, or where the middle works and the 2 on the outside, so the leftmost interval and the rightmost interval, don't work. Okay? So in this situation, we have that anything to the left of negative 2 would work. So x is less than negative 2. Or we have that anything to the right of 8 would work. So x is greater than 8. Now in this particular case, because we have a strict inequality, we see that our endpoints don't work, right? If I plug in a negative 2 or an 8, again, the left side would be 0. 0 is not greater than 0. So negative 2 is not a solution, and 8 is not a solution. So let me erase this and kind of drag this over here. We can write our solution also in interval notation. We could say that from negative infinity up to but not including negative 2, and the union with, we have anything larger than 8. Okay? So this is our interval notation. This is using x. We can also kind of graph this on a number line. So we could say, again, anything less than negative 2. I'll put a parenthesis at negative 2 to show it's not included. I'll just shade everything to the left. We also said anything greater than 8. I'll put a parenthesis at 8, shade everything to the right. All right, so that one was pretty easy. This one's also going to be easy, but just a little bit more tedious. So we have 25x squared plus 71x plus 16 is less than or equal to negative 7x squared minus x. So again, the first thing I'm going to do is write this as a quadratic expression on the left, 0 on the right. So I can add 7x squared to both sides of the inequality. And I can add x to both sides of the inequality. So this is going to cancel and become 0. Now 25 plus 7 is 32. So this will be 32x squared. And then plus 71 plus 1 is 72, so 72x. And then plus 16 is less than or equal to 0. Let's erase this, and we'll just kind of slide this up. Okay, so let's replace the inequality symbol with equals and solve that equation. So we're going to have 32x squared plus 72x plus 16 is equal to 0. Now each number in this equation, the 32, the 72, and the 16, are each divisible by 8. So 32 divided by 8 is 4, so this would be 4x squared. 72 divided by 8 is 9, so plus 9x. 16 divided by 8 is 2, so plus 2, and this equals 0, right? Obviously 0 divided by 8 is still 0. So let's erase this. Anytime you can make the equation simpler and work with smaller values, it's always a little bit better. So for this guy, I could solve it using factoring, or I can use my quadratic formula. Because this number right here is not prime, it's probably going to be faster to use my quadratic formula. So the 4 here represents A, the 9 here represents B, and the 2 here represents C. So my quadratic formula, in case you forgot, is x equals the negative of b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so negative b, we have negative 9 plus or minus b squared. 9 squared would be 81 minus 4 times a times c. Well, a here is 4, c here is 2. So negative 4 times 4 is negative 16. Negative 16 times 2 is negative 32. So this would be minus 32 here. Then we have 2 times a in the denominator. A is 4, so 2 times 4 is going to be 8. So then under our square root, we have 81 minus 32, which is 49. And the square root of 49 is 7. So we have negative 9 plus 7, which is going to be what? It's going to be negative 2 and then over 8. So we'll say that one solution is x equals negative 2 over 8, which we know would simplify to negative 1 over 4, so negative 1/4. Then the other solution would be negative 9 minus 7, and that's going to be negative 16, and then negative 16 over 8 would be negative 2. All right, so let's erase all this. We don't need this anymore. So we can see our two kind of critical values or boundaries are negative 1/4 and negative 2. So at negative 2, I could draw a kind of vertical line there. And then negative 1/4, we don't have a notch for it, but let's say it's about right there. So I'm just going to label this as negative 1/4. And let's just put a kind of vertical line there as well. So I'm splitting this up into 3 intervals. Anything to the left of negative 2 is interval A. Anything between negative 2 and negative 1/4 is interval B. And anything to the right of negative 1/4 is interval C. All right, so let's just pick a test value for each of these. And let me write my 0 there again. So let me divide this by 8. So this would have been 4x squared, and this would have been 9x, and this would have been 2. Again, just doing that so I have smaller values to work with. So I'm going to pick in interval A a value of negative 4. So let's plug that in there and also there. So negative 4 squared is 16. 4 times 16 is 64. And then 9 times negative 4 is going to be negative 36, so minus 36. And then plus 2. We don't even need to do the kind of operations here. We know that this would not be less than or equal to 0. So anything in interval A would be false. Okay, this would be false. So let's erase this. And now let's look at something in interval B. So again, the way most of these work, if something in interval A doesn't work, then B will work and C won't work, okay? So for B, let's pick negative 1. So let's plug that in here and here. So negative 1 squared is 1. 1 times 4 is 4. So 9 times negative 1 is minus 9. And then we have plus 2, and this is less than or equal to 0. We can tell that this is going to be negative on the left, right? So it will be less than 0. So we can say for interval B, it's true. And then again, in most cases, okay, not every case, but in most cases, if A works, the leftmost region, then B will not work, and C, the rightmost region, will work. So you have a case where kind of the leftmost region works, the middle region doesn't, and the rightmost region will work. The other case that happens a lot will be that the middle region works, and the one on the left and the one on the right don't work. Now, this isn't true every single time, but in most cases it follows this pattern, okay? So for region C, let's pick a value of 0, because that's going to be available. It's real easy to work with. So I'm going to plug in a 0 there and there. So we know this would be gone and this would be gone. You would have that 2 is less than or equal to 0, which is false, okay? So let's erase this. We have our solution region now. Interval B does work. Anything between negative 2 and negative 1/4. So x is greater than or equal to, because we have a non-strict inequality, negative 2, and less than or equal to, again, because we have a non-strict inequality, negative 1/4. Whenever you have that non-strict inequality, the endpoints are going to be solutions, okay? So we can show this in interval notation. Put a bracket here. We'll have negative 2, because that's included, comma, you'll have your negative 1/4, and then another bracket. So graphically, let me kind of keep that notch there for negative 1/4. Let's put that right there. What we're going to do is we're going to put a bracket at negative 2 and a bracket at negative 1/4, and just shade everything in between. So this is our graphical solution. This is interval notation. And then again, we can write this with our variable x and just say that x is greater than or equal to negative 2, and it's less than or equal to negative 1/4. All right, let's take a look at another one. So we have negative 2x squared minus x plus 3 is greater than 0. So in this case, I have my quadratic expression on the left and a 0 on the right. So I can just change this greater than here to equals and solve the resulting equation. So we have negative 2x squared minus x plus 3 is equal to 0. I can solve this using factoring pretty quickly. So I know that I can first divide everything by negative 1 so that the leading coefficient is going to be positive. That just makes it easier for me to factor. So I'm going to say this is positive 2x squared, and then we're going to have plus x minus 3 is equal to 0. Okay, so let's just erase this. And I can factor this on the left side here pretty quickly, because this 2 is a prime number. So this would be 2x and this would be x. I just got to work out the outer and the inner such that I get a plus 1x as my middle term, right? So the last term here is a negative 3. That can only come from a positive 1 times a negative 3, or a negative 1 times a positive 3. So if I want a positive 1x as the middle term, I would want to put a plus 3 here and a minus 1 here, right? Because the outer would be negative 2x and the inner would be plus 3x. If you sum those, you get plus 1x, okay? So I'm now going to set each factor equal to 0. So 2x plus 3 equals 0. Then or, I'm going to set x minus 1 equal to 0. So for this guy, I'm just going to subtract 3 away from each side of the equation. I'll get that 2x is equal to negative 3. Divide both sides by 2, and I'll get that x is equal to negative 3 halves. For this guy, I would add 1 to each side of the equation, and I would get that x equals positive 1. Okay? So I'm going to erase all this. I don't need any of this information anymore. I'm just going to kind of drag this up here. These are our critical values, or again, the boundaries of the endpoints. It's basically going to be the values that make this left side 0. Okay? So negative 3 halves, we can just say that's, again, halfway between negative 1 and negative 2. In decimal form, it's negative 1.5. So let's just say that's right there. So this is negative 3 halves. And then we have positive 1. So I'm just going to put a vertical line at each just to separate the number line into kind of intervals. So anything to the left of negative 3 halves, I'm going to call that interval A. Anything between negative 3 halves and positive 1, I'll call that interval B. And anything larger than positive 1, I'll call that interval C. Okay, so in interval A, let me just choose negative 4. So I'd have negative 2 times negative 4 squared minus negative 4, and then plus 3, is this greater than 0? So minus a negative 4 is plus 4, so we see that. We know that negative 4 squared is going to be 16, and negative 2 times 16 is negative 32. So we can see that this is not going to be greater than 0. So region A, we know that's false. Again, for most of these, not all of them, but for most of these, it sets up to where the one on the left, if that's going to be false, then the middle part is going to be true, and the part on the right is going to be false again. But again, you've got to really test these because you have some special case scenarios. So let's look at 0 for region B. So if I plugged in a 0 for x, this would be gone and this would be gone. I'd have that 3 is greater than 0, which is true. And then for C, let's just choose 4. So if I squared 4, I'd get 16. 16 times negative 2 is negative 32. And then minus 4 plus 3 is greater than 0. We can tell that's going to be false. Okay? Let's erase this. So basically, the region that works is region B. And we have a strict inequality, so the endpoints or the boundaries of the critical values will not work. So I can say that x is greater than negative 3 halves and less than positive 1. In interval notation, I would have my negative 3 halves next to a parenthesis, and then comma a 1 next to a parenthesis. Then kind of graphically, let me erase all this. I'm going to keep my notch there for negative 3 halves. So graphically, I'm just going to put a parenthesis at negative 3 halves and a parenthesis at positive 1, and then just shade everything in between. So this is my graphical solution. This is my interval notation. And then again, using x is greater than negative 3 halves and less than 1. So pretty easy overall to solve a quadratic inequality. As we move throughout our course, we'll see some more challenging scenarios. And we'll get to this when we start talking about graphing parabolas. Okay, so this would be the graph of a quadratic equation. We'll look at some more challenging situations with quadratic inequalities at that time. So we'll just wrap up our lesson by looking at some special case scenarios. And then as the final problem here, we'll talk about something that's not a quadratic inequality, but that we can use the same thought process to solve. Okay? So if we saw something like x squared plus 2ax plus a squared is greater than negative k, the idea here is that we know this is generic, but we can show that the left side here is a perfect square trinomial. So this can be factored into x plus a, that quantity squared, right? And this is greater than negative k. So don't get kind of tripped up by the fact that this is so generic, right? We have a negative k, we have an a. These are kind of foreign things when we see all these letters involved other than x. But again, don't let that kind of rattle you. All we're trying to say here is that in this particular case, I can plug in anything I want for x and I would get a true statement. Well, why is that? This guy over here, this negative k, just represents some negative real number. So it could be -3 or -10 or -2 billion, whatever you want it to be. Think about the fact that x can be anything and a can be anything, and I'll always get a true statement. X plus a can be whatever. It could be 0, it could be negative, it could be positive. Once I square this guy, if I square a negative, I get a positive, right? A positive would always be greater than a negative. If I square 0, I get 0. 0 would always be greater than a negative. If I square a positive, I'm going to get a positive, and that's always going to be greater than a negative. So there's nothing you can plug in for x that won't work. So if you see this scenario, you're basically going to have a solution where x is any real number. Okay, so you can say all real numbers. All right, let's look at an example. So we have 9x squared minus 48x plus 64 is greater than -5. So again, if you look at the left side and you have an inkling that this guy's going to be a perfect square trinomial, you check the ends, right? So 9x squared, that comes from 3x being squared. And then 64 comes from 8 being squared. So is the middle minus 2 times this guy, the 3x, times this guy, the 8. Well, 2 times 3 is 6. 6 times 8 is 48. 48 times x is 48x. And you've got the minus there. So this is minus 48x, right? So this is a perfect square trinomial. That means I can factor it into a binomial squared, right? This would be 3x minus, right, because you have the minus there, the 8, that quantity squared. Let me make that a little better. And this is greater than -5. Well, as we just said, this is going to be true for all real numbers, right? It doesn't matter what I plug in for x here. I'm going to multiply it by 3. I'm going to subtract away 8. No matter what it is, if it's negative or if it's 0 or if it's positive, when I square it, it's either going to be 0 or some positive number. So it's always going to be greater than -5. So this is true for all real numbers. So for this, I can just write all real numbers. Now, another thing I can do, you can kind of erase this. You don't need this anymore. You can write this in interval notation from -infinity to +infinity. You might want to do that. Or lastly, you can just shade the entire number line, right? So shade this arrow and then all the way through and then shade this arrow. Okay, so any real number would work as a solution for x in this scenario. All right, let's talk about the other scenario you're going to come across. So we have x squared plus 2ax plus a squared is less than -k. Again, the left side is a perfect square trinomial. So I can factor this into x plus a, that quantity squared. If I say it's less than the negative of k, so this is a negative number here on the right. So what happens is, if I choose a value for x, it doesn't matter what it is, I add some number a, and then I square that result, I'm always going to get something that's non-negative. So the left side here would be 0 or something positive. And that's never going to be less than a negative value. So when you see this, there's not going to be a solution. Now, if you get something like x squared plus 2ax plus a squared, and that's less than 0, again, this guy right here, this is x plus a quantity squared is less than 0. This would carry no solution as well. But if we change this and say it's less than or equal to 0, well, what happens is you would have one solution there, okay, in this particular case, because you could set this part right here equal to 0, and you could solve that. That would give you one solution, okay, one value that would satisfy the inequality. The less than part would never work, but the or equal to would work for one value, okay? So let's look at an example. So we have 49x squared minus 140x plus 100 is less than -2. So on the left side here, I know I can factor this into a binomial squared. This guy here on the left is 7x being squared. This guy here on the right is 10 being squared. And the middle is minus 2 times 7x, which is 14x, times this guy 10, which is 140x. So you have minus 140x. So this would work itself out to be factored into 7x. You have your minus there, so minus the 10 being squared, and this is less than -2. This will not have a solution, okay? There's no solution here. So there's no solution, okay? So you can put the symbol for the null or empty set, but again, no value here plugged in for x would give you a true statement. All right, so let's look at one more example here. And so what we have is the quantity x minus 1 times the quantity x plus 2 times the quantity x minus 4 is less than or equal to 0. So this, if I multiplied it together on the left, would not be a quadratic expression. It would be a cubic expression, right? So I wanted to give you one where it's not quadratic, and you can see that you can use pretty much the same process to solve it. So if you multiply this together on the left, you would get x cubed minus 3x squared minus 6x plus 8. Just went ahead and factored that already because we're not at a level where we can factor something like that yet. We'll learn how to do that later on in the course. So if I replace this inequality symbol with equals, I can solve the resulting equation. Because it's already in factored form, this will be pretty quick for us. So we know that our solutions here would be what? You'd have x minus 1 equals 0, so x would be 1. X plus 2 equals 0, so x could be negative 2. And then x minus 4 would be equal to 0, so x could also be 4. So these are our critical values here. So we have that x could be 1. So let's put a visible border there. X could be negative 2. And then x could be positive 4. So we're going to have 4 intervals here. So interval A will be anything to the left of negative 2. Interval B will be anything between negative 2 and positive 1. Interval C will be anything between positive 1 and positive 4. And interval D will be anything larger than positive 4. So let's erase this. I don't need any of this anymore. Let's just choose a point from each interval and see if it works. So for interval A, let's just choose negative 4. So negative 4 minus 1 is negative 5. And then negative 4 plus 2 would be negative 2, so times negative 2. And then negative 4 minus 4 would be negative 8. So is this less than or equal to 0? I don't even need to go through here and multiply. I know that a negative times a negative times a negative, basically 3 negatives, would give me a negative. A negative is always less than 0, so this part is true. So then for interval B, I can use 0, right? That's easy to work with. So 0 minus 1 is negative 1. 0 plus 2 is 2. 0 minus 4 is negative 4. So this guy, because there's 2 negatives being multiplied together, that would be a positive. So for interval B, that would be false, right? A positive is not going to be equal to 0, and a positive is not going to be less than 0. All right, for interval Z, let's choose 2. So 2 minus 1 is 1. And then 2 plus 2 is going to be 4. And then 2 minus 4 is going to be negative 2. So this guy would be negative, so this is going to work. This is true. And then for interval D, we can choose, let's say 5. 5 minus 1 is 4. 5 plus 2 is 7, so it would be times 7. And then 5 minus 4 is going to be 1. So everything here is going to be positive. Again, a positive is not less than 0, and it's not equal to 0. So for interval D, it's going to be false. Okay? So our solution here, again, because we have a non-strict inequality, the endpoints will be included. Anything in interval A, so anything to the left of negative 2, and also including negative 2. So x can be less than or equal to negative 2. Then or anything in interval C, so anything between 1 and 4 with 1 and 4 included. So x can be greater than or equal to 1 and less than or equal to 4. Okay, so those two kind of regions on the number line. So in interval notation, I can say from negative infinity up to and including negative 2. And it's the union with. We'll have anything from 1 to 4 with them both being included. So graphically, we can say that at negative 2, we'd put a bracket. We'd shade everything to the left. And then at 1, we'd put a bracket. And at 4, we'd put a bracket. Let me make that a little bit better. And then we'd shade everything in between here. Okay? So this is our solution graphically. This is our solution using interval notation. And then again, using x, we can say x is less than or equal to negative 2, or x is greater than or equal to 1, and less than or equal to 4.